Testing. Okay.
Turn it on there. Then
All right, I'm gonna wait 1 more minute to see if more people come, and if not, I'm gonna start. All right, so welcome everyone. Thanks for joining this presentation here in Seattle at the Embedded Linux Conference. And today I'm here to talk about the new major WirePlumber release, which is version 0.5, and how now we can use this new version to automatically handle PipeWire audio filters. But before jumping to the presentation, I'm going to do a quick introduction to myself. So my name is Julian. I'm from Spain, and I've been part of the multimedia team at Collabora since 2019. So I've been a software developer working on mostly open source multimedia projects such as GStreamer, PipeWire, and obviously WirePlumber. I leave here my email in case you have future inquiries. And with that being said, let's jump into the agenda. So as you can see here on the slide, I have decided to divide this presentation into 6 different sections. So first, I'm going to do a quick introduction to PipeWire and WirePlumber, because even though those projects are included by default in most of cutting-edge distributions like Ubuntu and Fedora and Arch Linux, a lot of people are still not very familiar with them, and they don't know exactly how they work. So that's for the first step. Then in the second section, I'm going to mention some features about this new major WirePlumber release, which was actually released just last month. So it's a very new release. And after that, I'm just going to focus on PipeWire audio filters. I'm going to explain what they are and how they are represented by PipeWire, and how this new version of WirePlumber can handle them automatically thanks to the smart filters policy. And finally, in the last section, I'm going to show an example of how we use this smart filters policy to solve a problem we face at Collabora when it comes to automatically switching Bluetooth profiles on the same device, depending on whether there's an application capturing audio or not. And if I have time at the end, I'm going to do a small demonstration showing a little bit of all of that. So that's for the introduction. Now let's start with the first section, which is intro to PipeWire and WirePlumber. So what's PipeWire? PipeWire is the next generation audio and video server to handle multimedia devices on Linux. So it's a user space daemon like Pulse Audio, but it also handles video as well. It's known for its exceptional performance and low latency, and it's built with security in mind, which makes it perfect for embedded devices, but also for desktop as well. But the most important feature, in my opinion, is that it has an external session manager. And now, the session manager is not included in the project itself because it's external, and it's the one that controls PipeWire and tells PipeWire what to do when an event happens. So that makes basically PipeWire adaptable for any use cases. When PipeWire was created, originally there wasn't really a reference implementation of an external session manager. So there was only an example which was mostly used to test PipeWire. So back in 2019, we had the motivation to implement a proper and reference session manager for PipeWire. And that's how WirePlumber was born. WirePlumber is currently the default session manager for PipeWire. It's sponsored by Collabora, and my coworker George is the original author of it. But I've been mostly working with him since the very beginning of this project. So as a session manager, it basically is the one charged to configure and handle PipeWire objects. So it basically configures device profiles and hardware routes. It defines access permissions between objects. It remembers all the user settings and preferences across reboots and restores them. And it's the one that is charged to decide what objects are linked with each other to form the processing graph. Because at the end of the day, PipeWire is a little bit like GStreamer. It basically has nodes, and there's links between those nodes to basically form the processing graph. And the most important thing about WirePlumber is that it's extensible, it's modular, and it's extremely configurable, because we want WirePlumber basically to work both on embedded and desktop. So it actually has Lua scripts that implement the actual management functionality. So if user wants to change a little bit of the behavior of WirePlumber, they can just write a Lua script, install it, and WirePlumber basically will adapt to each use case. If we have a look at the multimedia stack, we can see that PipeWire is this middle layer between the applications and the kernel. It basically, it's like a server where applications connect to it, and PipeWire then is the one charged to configure the device. The devices, like the audio devices, the video devices, in this case, Lib Camera, Video for Linux, Bluetooth. Also, so applications don't need to worry about checking whether the device is being used or whether they have to configure the device before they can use it. Applications, they just need to say, hey, PipeWire, I want to capture audio from this device, or I want to capture audio from this video, or I just want to play, audio on this device, and that's it. And as you can see here, WirePlumber is another daemon that runs in user space and communicates with PipeWire and tells him what to do when all these events happen. Now, the communication between all of these processes is done with Unix sockets. Yeah, it all runs in user space. Now I'm going to quickly talk about the WirePlumber 0.5 release. So it's a new major release. We've been working on it 2 years since 0.4 was released. 0.4 was actually the first stable release of WirePlumber that was included in major Linux distributions. This one has a clean API to hopefully last for a long time. So it's more like a 1.0 release. So if you're going to release 1.0 in the future, I don't think the API is going to change too much, hopefully. And it has plenty of new features. Now, some of the features is the event dispatcher, which is actually the most important thing. I have done a talk about this at the GStreamer conference last year, if you want to know more. But it basically, a feature that addresses many race conditions in a more robust and elegant way. Now, the configuration of WirePlumber compared to 0.4 has been moved from Lua to JSON. 0.5 still has Lua, but only for implementing the functionality. But so the configuration now is in JSON. Before, the configuration was also in Lua. And this is to keep more consistency with PipeWire, because PipeWire has a JSON configuration as well. Now, 0.5 also introduces the concept of settings. Now, users can change settings at runtime without changing the configuration and restarting WirePlumber. And these settings can be useful if the user wants just to quickly change the behavior of WirePlumber for a small period of time. And finally, which is what I'm going to focus this presentation on, is that it also introduces smart filters policy to automatically handle audio filters. So there's a blog post, if you're more interested about the new features of 0.5, done by George, my coworker, if you want to learn more. So here's the link. And status is the latest stable version is 0.5.1, which was a bug fix. The license is MIT. It's hosted on a free desktop GitLab. And like I said before, it's including major Linux distributions like Fedora, or Debian, Unstable, and Arch Linux. Now I'm going to jump on the second part of this presentation, which is I'm going to first explain what are PipeWire audio filters. So an audio filter, as you'll probably know already, is basically a processing unit that receives input audio signal, do some kind of transformation, and then outputs that signal to some device. In PipeWire, those audio filters, they are actually defined as a pair of two nodes. So each filter basically has one virtual device node and one virtual client node. And this is done like this because that way users can basically treat those audio filters as an application and a device. So users can use routing tools such as pulse audio volume control, for example, to change where they want to link it. So here, as you can see, if we have a sync filter, which is a filter that is meant to be linked with a sync device, for example, speakers, the virtual device would accept input buffers, and the virtual client would push the transform buffers to the actual device. And the same would be for the source filter, but in the opposite direction. So the virtual device would basically output transformed audio to the application, and the virtual client would capture audio from the real device, for example, a microphone. Example of already implemented audio filters in PipeWire are basically a loopback filter. Loopback is basically a filter that doesn't do anything. Some places they call it an identity. Now you might be wondering, why is this useful? Well, this is useful mostly to hide the real device. We're going to see an example of that later. Other example of filters is the filter chain, which is a module in PipeWire that is able to load already implemented filters from other projects such as LADSPA and LV2. And it also has some built-in filters. So usually this filter chain filter is used to implement some equalizers or compressors or limiters for audio. Now, there is also a noise reduction filter for voice. This is external. I think it uses the, I barely used it, so I'm not exactly sure how it works, but it basically uses the RN noise neural network to basically reduce the background noise. And finally, there's also echo cancellation. This one is implemented in PipeWire project. It comes by default to basically cancel audio. By the way, all these filters are implemented as PipeWire modules that are dynamically loaded. So if a user wants to implement new filters, they can just implement a new PipeWire module and install it in the PipeWire path to load the module. And then PipeWire will use it, and WirePlumber would work the same as with the other filters. So I'm going to explain quickly here echo cancellation because it's quite an interesting filter. So echo cancellation is actually a set of two filters. It has a sync filter and a source filter. So the way how it works is basically the sync filter monitors audio that is being played on the output device, for example, speakers. And then the source filter cancels the audio that is being monitored in input device, for example, a microphone, to basically cancel the echo. So it basically monitors the audio that is being played, and it cancels those frequencies that are being monitored. Now, this filter doesn't really make sense to be used if a user has a headset, because nobody can hear audio, and if nobody can hear, only yourself can hear it, there's really nothing to cancel. And this was also one of the motivations why we decided to implement a smart filters policy, because we only want to use specific filters only when specific devices are being used. So up until now, manual user intervention with WirePlumber was needed when we wanted to basically use filters for specific devices. By default, when you are running WirePlumber, the filters, they are always used with the default input device or output device. And if a user didn't want to use them and they want to use them only for a specific device, it was quite cumbersome because they had to change the target of those filters manually using tools such as WirePlumber control or pulse volume volume control or even Carla. And this was quite cumbersome. So we had the motivation of automate this task in WirePlumber 0.5, and that's when we decided to implement the smart filters policy. So now I'm going to explain how to use it and how flexible it can be. So WirePlumber 0.5 introduces several properties to basically control this automation. So the first one is a filter.smart, which is a Boolean value. By default, it's set to false. So this means that by default, it's not gonna do any automation without filter. But if it's set to true, it basically marks the filter as smart and is gonna try to link it properly, like the user wants. Then we have the name property, which is a unique identifier for the filter. Then we have a before and after properties that allows specifying what filters are meant to go before this one and after this one. And finally, we have the target property, which is the most important one, and is basically the one that needs to be set with the properties matching the final target node in the chain. So this property is basically meant to group filters together that want to be linked with the same target. I'm going to show an example of this later, because it's a little bit hard to understand just like this. Anyway, those properties can be set in the JSON configuration of the filter so that they are permanent, like in this example. But they can also be changed at runtime easily using the filters metadata and the PW metadata command. So here is an example of two filters that are chained together always, and they are always linked to the microphone. So we have, an echo cancellation source filter, and we also have a noise reduction source filter. Now, like I said, these two filters don't make sense to be used with any other device that is not a built-in microphone, for example, on a laptop. So the properties, as you can see on the left, are name echo cancel. It needs to run before noise reduction, and the target is the microphone. And for the noise reduction source filter, the properties are name noise reduction. The after property is set after echo cancel, so that it's not used before. And the target is also microphone. So when they have the same target, they are chained together, and they are the order of processing is defined by the before and after properties. And it's always linked to the microphone, which is the top left node. And then any recording applications that want to record from the microphone, they're going to be automatically linked to the noise reduction source filter. So now I'm going to explain how we use this policy to solve a problem we face at Collabora when it comes to automatically switching Bluetooth profiles. So Bluetooth is very complex. There's a lot of profiles. But most of Bluetooth devices, they have an A2DP profile, an HSP or HFP profile. They have those two profiles. So A2DP is basically high-quality audio, and it's only meant for playback, usually to listen to music or something like that. And HSP is usually for video call applications. It's low-latency profile, and it supports both capture and playback. So when you connect a Bluetooth device, PipeWire, what it's going to do is, if it's configuring A2DP profile, it's going to just create one node. But if the user changes the profile to be HSP, it's going to destroy the A2DP node, and it's going to create two nodes, one sync node and one source node for the HSP profile. And if you switch back, it's going to destroy those nodes, and it's going to create new nodes. So this is this can cause a problem for applications, because since there is no Bluetooth source node, when the A2DP profile is selected, applications can't know if the Bluetooth device supports HSP profile. So we cannot know if we want to switch to HSP or not. The previous version of WirePlumber, the 0.4 series, had some weird logic to work around this. It was basically auto-switching to HFP profile if the client with specific names, such as Zoom or even Firefox or Chrome, applications that are meant to be used for video calls, want to capture audio when the current Bluetooth device is configured as the default device. But this caused some problems. For example, if users were connecting multiple Bluetooth devices on your system. So ideally, what we want to do is we want to use only A2DP profile when there is no application that wants to capture audio from the Bluetooth device. So how can we do that? And the solution is basically to add a loopback filter for each connected Bluetooth device. Oops. Yeah. So basically, the logic works like this. WirePlumber creates one loopback source filter per connected Bluetooth device that supports HSP profile. And that source filter basically has the same name as the HSP source node of the Bluetooth profile. And it's just there to let applications know that there is a node that can output buffers. Now, the target of this loopback filter is set to the real HSP source node of the device, if any, because if it's set to if the device is set to A2DP, there's no HSP source node. Then the actual HSP source node is always hidden from applications, so that applications don't know there's like two source nodes for that Bluetooth device. And then HSP and A2DP profile auto switch happens when a client node starts and stops capturing audio from the loopback source filter node. I'm going to explain this in a demonstration at the end. It's easy to understand. But I draw here a small diagram explaining how this works. So let's say you connect a Bluetooth device, and the profile is set to A2DP. So there's only one node, and you have the playback application that is sending buffers and is playing basically music on your Bluetooth headset. However, as you can see on the right, there is a loopback filter that exposes a source node, and that source node has exactly the same name as the HSP source of the Bluetooth device. And the virtual client without filter is hidden. That's why it's gray there. So applications don't know anything about that. So regardless of which profile it is enabled, application will always see two nodes. And if an application starts capturing audio from the filter source node on the top right, the red box on the top right, WirePlumber is going to basically switch the Bluetooth profile to HSP, and it's going to link the virtual client node to the actual HSP source node. Those two nodes are always hidden. That's why they are gray and not red. So yeah, when you switch profiles, applications, they really don't know the difference because they always think there's always two nodes available. Now, the advantage of having this is that Bluetooth profile auto switch just works out of the box. So applications don't need to worry about what Bluetooth profile is set on any device. And it works with multiple connected Bluetooth devices, even if they are not configured as the default device. Now, any applications can also capture from any Bluetooth device without user intervention. And there's no need to rely on hard-coded application names like I mentioned before. I think that's it. Let's see if we have time for the demonstration. I'm going to do a quick demonstration now because we have time. So as you can see here, I have a terminal on the left. I'm running Arch Linux, by the way, which runs WirePlumber 0.5.1, as you can see. And on the right, I'm running Helvum, which is just a graphical. It's just an application to show the current PipeWire objects. So, for example, if I run, oh, by the way, I want to show that. So if I show basically the processes running, you can see that I'm running PipeWire, I'm running WirePlumber, and I'm also running PipeWire Pulse. Now, PipeWire Pulse is yet another daemon that basically translates the Pulse audio requests into PipeWire requests, and this is needed so that basically any Pulse audio application can work with PipeWire. So yeah, thanks to this, I can, for example, use PipePlay to play audio, for example. I don't know if you can hear this. And you can see here that the client is connected basically to the speakers node on the right. Oops. So I can also record, power record, out.wave. Testing 1, 2, 3. Cancel, and I can play again. Testing. Yeah. So anyway, now I have a Bluetooth headset here, and I'm gonna. It's already paired with the laptop, so I'm just gonna connect it. And we're going to see how the profile auto switch is going to work. All right, so it should connect in a few seconds. We should see some nodes coming up on the right. All right, so here it is. It's basically a regular Bluetooth headset. It has a built-in microphone, and it has headphones. And it supports both A2DP and HSP profile. So if I run now, for example, Power Control, which is a tool to configure devices and clients, we can see that the Bluetooth profile is already set to A2DP. But we can see here that so that's the filter that is there, even though it's in A2DP profile. We can still see that there's some node that application can capture audio from. So anyway, it's A2DP profile. If I play something, we can see that the client is linked with the headphones, and there's audio playing here. You can hear it, but it's definitely playing something. You can actually see the activity here on the bottom that is playing on the JVC headset, and the profile is still A2DP sync. So I'm going to cancel that, but now I'm going to capture audio. I'm going to do power record, and you can see here that power record is actually getting audio from the the virtual device, and then the virtual client is basically capturing audio from the real Bluetooth device. And you can see, and this is possible because WirePlumber automatically switched the profile to HSP and HFP. So if I cancel it, we can see that the profile has switched back to HTTP because we don't want to use it because we are not capturing. So yeah, anyway, this is possible thanks to the smart filters policy in WirePlumber 0.5. And that's basically it. Are there any questions? Yeah.
Thank you. Is the PipeWire filter implemented as a PipeWire plugin, or is it an external process, or
no, it's the same. Yeah, so the question is if PipeWire filter is a plugin, right? And if it's an external process. No, so PipeWire is not multi-process. Sorry, PipeWire it's a daemon and it runs everything in one thread. So the filters are basically a module that are dynamically loaded, but then they are just used on the same thread as the rest of the graph.
Thank you.
Any more questions? All right, that was easy. So thank you for coming, and I hope you enjoyed the presentation. Hello.
I want to ask you if you know any open source libraries for
All right. I don't think we're getting anyone else. Okay. Hi, everyone. Thank you for joining me today. I know I'd rather be upstairs listening to Pavel talk about test automation, so I appreciate everyone taking time to be here. Yeah, this is my first time on the conference circuit. If you're all still awake when I'm done, I'll take it as a win. So I'm Matt. I come from Imagination Technologies. For the past 4 years, I've been working on the open source driver for our PipeWire GPUs, which is very exciting. It's nice to be able to finally work on that out in the open. I thought I'd start today with a literal overview of a modern DRM driver. As you might expect, the story starts with a GPU. Throughout our early development on the open source driver stack, we've been focused across a few different GPU models, but the one we've made the most progress with so far is our AXE 116M. More specifically, we've been using AM625 development boards from TI. The whole AM62 family of SoCs uses this same GPU. But this dev board in particular is cheap and simple, and we have way too many of them now. That monstrosity does serve a real purpose. It's helped us run countless CTS iterations to achieve full conformance on that chip for Vulkan 1.0, which is very exciting, and that's a huge step towards becoming a mature driver. And we can finally use the logo. So our GPU, on top of that GPU sits our driver stack. I'm sure you've all seen this kind of overview diagram before. I won't go into too much detail, but there's one thing I really want to point out here. The user space section is specifically labeled Vulkan. This is deliberate. Our driver stack has been developed from the ground up to be a Vulkan driver and implement that Vulkan API. So OpenGLES, OpenGL, desktop, that'll come from the Zinc layer in Mesa, which implements them on top of Vulkan, as long as we implement a bunch of extra compatibility extensions, which we weren't expecting. I think that's an overview. I guess I'm done here. No. Okay, so there are two relatively new components in the DRM subsystem that I'd like to talk about today, GPU VM and the DRM scheduler. And let's start with the scheduler. It's not actually that new, so I think brief history. The earliest version landed in the AMD GPU tree almost a decade ago, way back in 2015, which makes me feel very old. 2 years later, Lucas Stack recognized the marvelous AMD GPU scheduler and worked to move it into DRM common code with an initial prototype of the Etnaviv driver already using it. Over the next 2 years, 3 new GPU drivers landed in mainline Linux, all of which made use of the DRM scheduler from the outset, with 4 drivers now building on top of the common code, plus AMD GPU from the outset. Some deficiencies started cropping up. Simaveta noted a major one in 2021. All drivers had to hand-roll their own dependency handling. Patches were sent out, and soon all 4 drivers were using common dependency handling in the scheduler as well. So there's a great pedigree there, and it really sounds like we should be taking advantage of this framework when developing a new driver rather than re-implementing from scratch. And that's not just a flippant comment. Many people feel, and we agree, that it is important to add or reuse common code where appropriate in order to keep a unified ecosystem moving smoothly forwards. Having 7 different implementations of a scheduler is just asking for maintainers to give up and leave. So, okay, let's get that GPU scheduler plumbed into our driver. There is a snag. PowerVR GPUs have firmware, which they use to do scheduling directly on the GPU with little involvement from the driver stack. And that's okay. The DRM scheduler is just a framework. So if we don't need the software scheduler, we just won't use it. It turns out the DRM scheduler doesn't just schedule. It does a bit more than that. It also enforces the often subtle and arcane semantics around DMA fences, which we do not want to get up to try and do ourselves, I had no interest in messing it up myself, so we need to figure out how to make the DRM scheduler and our firmware scheduler play nice together. The most obvious solution would be just dumb down the firmware enough that the DRM scheduler can do its work without the two conflicting. This is technically possible. We could have done this. The end result would be not exactly ideal. We would lose the benefits of offloading scheduling work to the firmware, which includes reduced latency of resolving dependencies at critical time, and just lower workload on the CPU. But it would mean our firmware fork diverging significantly from the proprietary driver. Timing was on our side here. After 2 RFC versions, our driver with no DRM scheduler support, Matt Brost from Intel, published an RFC entitled Z DRM Scheduler and Long-Running Workload Plans, which started with this familiar sentiment. Hey, that sounds pretty familiar, right? That's what we're trying to do. Did we miss something? Is there something there already that we could have used? No, this is all brand new work that he's been working on. Their solution, as suggested by, I believe, Faith Ekstrand originally, was to bind schedulers to entities one-to-one. Okay, back up. What's an entity? Let's back up and talk briefly about the architecture of the DRM scheduler. At the time of the Z-Patch series, the DRM scheduler consisted of a 4-layer structure. Each GPU hardware queue is assigned a scheduler. Each scheduler maintains multiple run queues. Each run queue corresponds to a task priority, so ranging from kernel priority at the top, high, normal, low. The driver submits entities to queues based on priority, and each entity holds a queue of strictly ordered jobs. The glue that makes this whole layer construct useful is 2 rules. So the first rule is an invariant. Jobs in an entity are always executed in order. The entities themselves have no direct relation to each other, but within a single entity, those jobs are guaranteed to execute sequentially. And second, a scheduling rule. These define how the entities are arranged in run queues, and essentially there are 2 options, FIFO and round robin. In FIFO, the run queues are strictly ordered. Each entity has all its jobs executed in full, and then the scheduler moves on to the next. In round robin mode, the run queues are strictly unordered. Jobs are selected from each entity in turn, as you would expect from round robin. In both cases, empty entities are skipped, but for all intents and purposes, this is also an invariant because you can only configure this system-wide at runtime. So, one-to-one relationship between schedulers and entities. All right. Other Matt's solution was a new special option, DRM shed policy single entity, which is a mouthful. When enabled, that would eliminate the run queues entirely, instead assigning a single persistent entity to each scheduler, with all jobs being added to that entity. So with only one entity in play, So with only one entity in play, the 2 rules from before allow us to ensure that all of the jobs ever submitted to that scheduler would run in the order they were submitted. So from the first, jobs in an entity are already executed in order. Yep, we know that. That's easy. We've only got one entity. Everything's in order. And the scheduling rule becomes irrelevant when you only have one entity to choose from, because both will always choose the next job from that single entity. This really does sound like it simplifies things a lot. And from a consumer point of view, it does. If this was the only case, unfortunately, the implementation was kind of a mess and required putting if single entity checks all over the code for the scheduler, and it was a bit messy. A lot of special casing going on. So each run queue corresponds to a predefined, bear with me a second. As is often the way in the world of open source, this was not the solution that ultimately landed. After months of discussion and changes around that original Z patch series, Luban Twikov of AMD proposed an alternative by way of fixing one of the early limitations of the scheduler. So recall we have 4 run queues, that's fixed, and each run queue has a fixed priority. Luban's change was really simple in concept. Just let each driver define its own list of priorities, and crucially, each driver announces how many run queues it requires per GPU scheduler it creates. So now we have a way to frame the firmware-aware scheduler solution, whereas the introduction of DRM shed policy single entity required one large change to the DRM scheduler itself. The new solution made possible by this change from Luban consisted of just 2 small steps taken by the implementing driver. Declare only one priority, which prevents the DRM scheduler from prioritizing any job over any other job, and declare only one entity. Since we only have one priority, that means we declare one entity per scheduler. And that was the other Matt's original solution. So the same application of those 2 rules applies here. Jobs are always executed in order in an entity, and we don't have to worry about the entity arrangement because there is only one. So that is our solution for the DRM scheduler, and that is the end of our story with it. Let's switch over now to the GPU VM. GPU VM was born as the GPU Virtual Address Manager, shortened to GPU VA Manager, shortened to GPU VA, which just was meaningless, so it became GPU VM. The brainchild of Dan Lowe-Krumrich and Dave Airley, both of Red Hat, it is intended to help drivers implement user space manageable GPU virtual address spaces in reference to the Vulkan API. Now that sounds really good to us. We're a Vulkan first driver. Of course we want something that'll help us implement the Vulkan API. Much like we talked about with the DRM scheduler, GPU VM is designed to solve a problem that most, if not all, DRM drivers encounter, managing the virtual address space, or spaces, of a GPU. The first version of the GPU VM patches was sent out after our first RFC patch for the PowerVR DRM driver. So just from the patch summaries, we can see one of the benefits it gave us. Less code. Yeah. Other, excuse me. Nope, I've lost it. Okay. I seem to have lost the rest of my slide deck. I don't know where it's gone. So we will ad-lib from here. The other benefit of the GPU Virtual Manager is that it can allow us to do, well, it basically provides 3 functionalities. It provides allocation of the address space, which is not a new thing. There's already a system in the kernel to do that. But what it also does is define this mechanism for mapping physical memory into it. So that is primarily through the lens of GEM, the Intel's original memory management system, which we were already taking advantage of. And third, and most crucially, it allows you to perform complex operations on those 2 structures that are storing information about the address space and how it's mapped into hardware. And some of those complex operations are very error-prone, and people tend to get them wrong implementing them themselves. So that's where the bulk of that code that we stripped out there came from, or went away, I guess. So these operations are things like splitting an address range so that you can partially map or unmap. You could create a sparse binding where you have a large virtual address area and only certain parts of it need backing memory. So you would only map the bits you need, and all this complexity is just more information that needs to be tracked. You don't want to be reinventing the wheel, so GPU VM. So why are we bothering with all this? This is a lot of work, seemingly. As mentioned earlier, it's important to reuse code where possible, and just copy-pasting it into your own driver is really not the way to do that. You end up with 2 separate sets of problems. Someone will fix one somewhere, the other one doesn't get fixed, they diverge, features are added, features are removed, optimizations are added. It's just a nightmare. You don't want to be doing that. So when I say reusing code, I mean lifting code out into common library space so that multiple sections of the kernel or of whatever project can take advantage of it. With the GPU scheduler, this was the path that was taken. It was lifted out of AMD and made common for everyone to access. With GPU VM, it was created from the outset as a common library, but it solved a problem that already existed, or that had already been solved by the drivers that existed at the time. I guess the idea with, no, the new functionality that the GPU VM provided was something that didn't exist in any of the drivers at the point, and it backed something that NVIDIA or the Nouveau folks called VM bind, which was how all of these complex operations like sparse binding, partial mapping, were exposed to user space to allow Vulkan to take advantage of them. And I guess they looked at the existing solutions and went, none of these are good enough, let's do something better, and then everyone can use it. And that's where we are. We have this fantastic memory manager. We were involved in the development. As I said, our first patch went out right before this came out, but our later versions came out after. So while GPU VM went through 7 or 8 patch iterations, and our driver went through more, we were able to test, review, and suggest changes to the GPU VM code as it was evolving, and then keep our driver updated with it. Which brings me to one of the problems we had. When developing against bleeding edge features, like these new strategies added to the DRM scheduler or the GPU VM code, you're working against patches. You're not working against a Git tree. And that can be pretty frustrating. Not just from a tooling perspective. There are scripts, there are tools that can fix this or make it easier to work with patches. That's fine. The problem is the moving target. GPU VM, as I said, went through 7 or 8 revisions. The DRM scheduler changes went through, well, there were a lot of changes. It was around for 10 years. But the changes to do with the firmware were happening at the same time as we needed to use them. So as those patches are reviewed, changed, updated, bugs fixed in them, we had to keep up with that. And often that meant API surfaces changing significantly between releases. So the major challenge with keeping using modern, like really modern bleeding edge library code, common code, is keeping up with it. So is it worth it? Should we just not use the new stuff, let someone else deal with it first and use it 5 years, 10 years down the line once it's mature and the standard already? Well, someone's got to go first. Someone's got to deal with it. And if no one's using the common code, it'll never get tested, and then it'll never get landed. There's no reason to have it. You've got a chicken-egg problem. So it is important for someone, ideally everyone, to get on board at the start. And that is how we drive these things forward, by using the new features as they come available and interacting with the people creating them, adding your use case. This is something that I heard mentioned in an unconference yesterday, is that the more consumers of common code you have, the more edge cases become core use cases. And edge cases are notoriously painful to test, but if you have multiple sets of use cases using the same code, you have more ways to test that code, you have less ways to get it wrong. So it's important to use common code, it's important to use new common code, and it's important to create common code. We haven't had the opportunity to do that yet, but that doesn't mean we won't. There's a long way to go before our kernel driver is complete, whatever that means. I'm sure it will never be complete. We'll always be adding things to it, adding functionality, or bring up for new devices. And hopefully along the way, we will get a chance to contribute back what we've taken from the community. So we will hopefully be able to do our own something, DRM scheduler, GPU VM, who knows what the future holds. But it is exciting, and hopefully everyone will work together on these projects, and we can keep moving DRM forward. That's about all I have to say. Thank you. Yeah, I guess questions? Yep. There you go.
I guess following off the theme of scheduling being moved into the firmware, do you foresee more and more of like driver functionality being moved onto the firmware side, and or it's like usually closed source? And I guess like a second part of the question is, do you see like a viable future where like open source GPU firmware becomes somewhat common?
Okay. So I'm going to back up and answer a separate question that you didn't actually ask first. But we are not the only people anymore who do scheduling in firmware. That seems to be the future. The Z driver that I mentioned earlier, all of that new Intel stuff is doing scheduling on firmware. ARM is moving towards it with their newer chipsets. It's not going away. The benefits of doing scheduling on the firmware are that low latency I talked about. You can resolve fences and dependencies between jobs directly there without going back and forth between the kernel and the hardware. So I think there is always a compelling reason to do that there. In terms of moving other functionality in, I'm not sure what you would be able to move into firmware. The scheduler is a fairly obvious one because of that latency, but by the time you've moved that in, you essentially just have work being thrown at the GPU, and that's the only operation you need to do really with it. So the future of firmware, personally, I think it would be great to have open source firmware. That is not my call. The future of open source firmware, I think someone's going to have to take the first step. I don't know if that's going to be us. It could be someone else. But I think once at least one company does it, then maybe others will follow. But there could be a lot of secrets revealed. I don't really know much about our firmware. I've never worked on it. But it's entirely possible that there's stuff in there that companies would consider proprietary and too private to share. So maybe you'd get a simpler firmware, maybe one without the scheduler, and rely on the DRM scheduler to do the scheduling properly. I don't know what that looks like. Sorry. Yeah, can you pass it back?
I guess one of the concerns with closed source firmware is if the firmware is the one programming the MMUs and responsible for containment of what the GPU can and can't access, then that closed source firmware is a little scarier. If there's somebody else that the kernel is supervising an MMU that he has control over, and so the GPU is contained, then it's a little less scary. What's your architecture there?
Regarding the MMU, so that's controlled directly from the kernel. It's the I'm trying to remember. Yeah, so it's a shared memory area where you program effectively. I believe ours is a 3-layer page table, and it operates just like your CPU page table, where the CPU is setting everything up, and the GPU reserves small sections of that memory for firmware operations, because of course the firmware needs some memory to function. But for the most part, all of that has to be allocated by the CPU, and then the firmware is told which bits it can use. So it is very much kept in a box.
Okay, great, thanks.
No? Yeah, okay.
Say you wanted to do like GPU development for, I don't know, some Pine 64 board or something.
Yep.
Like what's the basic hardware setup you use for that? Like, do you really need like a stack of like 15
No.
boards?
So the Vulkan Conformance Test Suite is enormous. There are millions of test cases. So we split it up across as many devices as we can every time we run it, so that the developers on the team can get quicker results back. It's also a very complicated conformance test suite. Things intermingle. The tests don't necessarily just test the thing they say. So it's very easy to break tests that seem completely unrelated. So you do need to run the whole thing over and over again. For the first 2 years of our work on this project, I would say, we didn't touch CTS. We focused on getting a really simple Vulkan demo up, and the Sasha Willems demos, which became, I believe, the Kronos official demos now. Those are great. There's some really simple stuff in there, and you can see exactly which Vulkan calls are being made. So that's a great way to do startup development on a GPU driver, is to try and run simple examples. There are some simple bits of CTS, but the overhead is just enormous. It's a huge pain. Yeah, so simple demos. You only need your one device. You don't need lots. If it's a new GPU that no one's written an open source driver on before, you may have difficulty. You need a fair amount of information about it. It's a complex beast. It's like programming a CPU. You know, it wouldn't be possible without the huge data sheets from ARM, from Intel. So you're kind of at the mercy of companies to provide that information. And then with firmware becoming more prevalent, you need the blob from somewhere. In our case, the firmware blobs that the open source driver uses are subtly different from the ones from the proprietary driver. So even if you get hold of a leaked copy of one of those from somewhere, it's not going to help you, I'm afraid. Oh, sorry. Yeah. Thank you.
Hey.
Hey.
I had 2 questions. Thank you,
Great.
first of all, but I had 2 questions.
Okay.
The first one is, there was some news lately about like AMD not open sourcing firmware, but entertaining open sourcing the documentation for that firmware. I was just wondering if you heard about that.
I haven't heard about that. That would be really cool.
Yeah, there's
AMD are quite big in the open source space.
Yeah.
I know a lot of the developers on it. I mentioned a couple of them in the talk, right? Having open source documentation for the firmware interface is one of those crucial bits that you need for writing a driver. It's just as important as having hardware documentation, right? Because if you know what registers to write into, for example, you can program the hardware, but you can't interact with the firmware without knowing what the ABI looks like there. So yeah, that's really cool if they're actually doing that.
The other question was, apart from GPU VM and the DRM scheduler infrastructure,
Yep.
I was wondering what other common infrastructure patterns there are. I heard that Faith Eriksrad is looking to make like a common infrastructure for Vulkan, at least I think like Mesa UMDs.
Yes.
I was wondering if there was a similar track for DRM in other spaces. Like what other?
Okay.
Yeah.
So the story in user space is much, I don't want to say simpler, it's still complicated writing a Vulkan driver, but it's more straightforward to see how code could be made common. In the kernel, you're interacting with wildly different hardware that behaves in very different ways often. That's tending to be less true now that you've got more low-level APIs, DirectX 12, Vulkan, and newer hardware is being designed around those APIs, and the APIs are designed around the hardware. So you have more commonality now, which is why the scheduler, GPU VM are now possible to be common. In user space, I don't work on the user space, I only work on the kernel bit. But from what I understand, the current state of the Vulkan common code in Mesa is it's more of a toolkit that drivers can opt into bits that they need and want to reuse, rather than a framework that the drivers sit in. There is talk from Faith about flipping that upside down. That is how, I forget what it's called, the layer that Zinc sits on top of Vulkan. There's a compatibility layer in the middle there, which is a custom API that exists only in Mesa, and it allows front ends to talk to back ends. So you have a GL API, you have a GLES, you have a WebGL, whatever other APIs you need.
Translation layer?
Yeah, exactly. And the concern with moving Vulkan to that kind of model, where you have a framework that provides the Vulkan, all the runtime details, is that you'd effectively have to re-implement Vulkan as a compatibility layer on top of that. and then what's the point, right? You're not actually gaining anything. You're just creating a new complicated API. So I think the current state of Mesa with a Vulkan runtime that is opt-in is good. Obviously, the more you opt into it, the better. I've already advocated for reusing common code, but it's got to be up to the drivers because some stuff just doesn't make sense for everyone.
So with DRM, it's a little bit harder to create that.
In the kernel, yes, it's absolutely, yeah.
Yeah.
The UAPIs can be made somewhat similar, that bridge to user space, but there's still, like there is common DRM UAPI ioctls, but not all of them can be made common. There's always going to be device-specific stuff that you need. Okay. And I think if you tried to make it all common, you just end up reinventing the concept of ioctls inside ioctls, which, again, seems a bit pointless. Yep.
Oh, where? Oh.
That's like 3 questions already.
Oh my.
Come on, take up the slack, people. I guess I'm interested in your career development and like how you end up working on GPU drivers. It's interesting to me.
It's where I started. Yeah, that's it, day one. No, I came out of uni and I went straight into Imagination. I was the first person brought onto the open source project. So it was kind of a really unique position available at the time to work on an open source project at a company where I could get a stable job out of it as well. It was kind of too good to be to turn up. And the fact that it was on a GPU driver was, okay, great, I can learn this. I can figure out what I'm doing here. I started out on the kernel side. We brought more senior people on for the kernel side. I did a bit of work on the Mesa side while they did all the hard stuff that I didn't understand. And now I'm back on the kernel side. Yeah, so I've kind of seen a lot of the driver stack. It's been a steep learning curve, that's for sure. I still don't understand a huge chunk of how Vulkan works. But you don't need to understand everything, right? That's why you have a team around you.
So now that you have like Vulkan 1.0 compliance,
Yes.
What's the future plans? Like, is the plan to complete Vulkan 1.1 or like support other GPU cores?
So I've been told I'm not allowed to talk about our roadmap.
Okay.
I'm sorry. Yeah. Basically, there's a lot we want to do, right? And we can't do it all at once because we are a small team. There's only 5 or 6 of us. There's a sort of fantasy from companies about open source that means, oh, you can just get the community to do it. But no, someone's got to do the work, and it's the people who work for the company that are going to end up doing the work, right? So we're going to be the ones doing most of the work towards 1.1, 1.2, or new hardware, or whatever. What I'll say is we have released a handful of firmware binaries for other platforms, so it's not just this one. We've also released the device info for those platforms, so a list of features, hardware features, and lists of errata, which errata apply to them. That all exists in a branch in our GitLab repository for Mesa. So with that information, it is possible to bring up those devices, provided the features support exists, which it does for most of it, as far as I'm aware. And yeah, so I mentioned at the beginning Zinc being used to support GL desktop and GLES. We're not there yet. We are working on it. That I will say, because we are missing some of the extensions. It's Vulkan 1.0 plus a handful of extensions that make Vulkan behave more like OpenGL. Yeah, it's controversial that way that was done, but yeah, that's about all I can share. Yep.
How's your performance for the closed source versus the open source driver?
We don't have performance numbers yet. We haven't really been, like, obviously we're thinking about performance in the back of our minds while we're writing code. We're not just doing everything in like ON cube time or something, but it's not our priority right now. Our priority is feature completeness, trying to get everything working at all, and then we can go back and really focus on performance numbers later. I don't expect that it's on par at the moment, honestly. But that doesn't have to be the case forever, right? It'll improve.
Thanks. So I guess on that vein, what was the motivation for writing an open source driver in the first place? If you say that, you know, employees of that imagination are still writing said driver, what's the motivation for making it open source? What was the driving factor for that?
So even if it's not open source, we still have to work with the kernel. So we still have to write a kernel module. It just is an out-of-tree kernel module or an in-tree kernel module on a fork, something like that. And we still have to do user space. Part of it is just not wanting to do everything ourselves in-house. People have already done things. They've already done them well. Why can't we take advantage of that? And that's kind of the selfish view of it, right? It's it just makes good business sense to reuse code that exists. My manager started pushing for this project for years, and he really wanted to get this off the ground. And it wasn't until, well, the driving factor essentially became, we want to take advantage of new features. We need to be closer to the development. We need to be upstream. We need to be in tree. And that eventually became our motivation, or that was the business motivation, because we did have to convince. They're not just going to do it out of the goodness of their hearts, right?
Yeah.
It's but yeah, that's kind of the approach that they took.
Yeah, I was just contrasting to NVIDIA and their proprietary drivers.
Yeah.
Yeah.
Oh, you got more. Yeah, you're keeping it going. Yeah.
So actually, I kind of missed the fact that it was a closed source driver and then you wrote an open source version.
Yeah, so it's kind of been a historical thing in the community that PowerVR drivers were never open source. In a lot of cases, the open source drivers in Mesa and DRM were written by the community. They didn't come out of the companies that created the hardware. There are a few exceptions to that, but for the most part, they're reverse engineered efforts, or they're done from docs released by the companies, but they didn't want to do the work. So it's really nice for us to be able to be an exception there. It's had some interesting challenges, mostly around licensing. We're looking at the proprietary code all day long. It's like, how do you firewall it? And we had to firewall it. So the code that we've upstreamed is all written from scratch. It's not just cut and paste from our proprietary driver. You can kind of see that. A few years ago, we released the source code for one of our earliest graphics drivers, just out of historical curiosity, I think. So you can see they're fundamentally quite different. And it was it's a good opportunity to get a clean break and start from scratch and build on what everyone else has been working on in the meantime.
Can you talk a bit about like what the firewall process looks like?
Probably not. I will probably get in trouble. Yeah, there's one behind you there.
Is there any plan to go and do functional safety with graphics?
Okay.
Is there any plan to go and do functional safety compliance with your graphics driver?
Yeah. The proprietary driver is available for Vulkan Safety Critical.
Open source.
I know. I'm getting there. The proprietary one is available for Safety Critical. As far as I know, nothing in DRM or Mesa is built for functional safety. There are no open source Vulkan SC drivers that I'm aware of. I don't think that's going to change anytime soon. Yeah, I'm sorry. That's probably not the answer you want to hear. Nope. Okay. Should we leave it there?
Thank you.
Yep. All right. Hello?
appreciate it. So like, I'm very committed to like making this like a career path for me. So I'm mostly in cloud right now. I do content delivery services, but big transition. So like, I have a GitHub. This is just one of the directories. So that's like the repository. So I have like several for like graphic Joshua. But like, this is desktop directory.
I live right here.
So I have like lots of like markdown files and like notes for the entire graphic. Yeah, these are all images from like presentations from
So,
and stuff like that.
on Thursday night, there's a bar on Capitol Hill that B-Sides meets at. So some of the security guys meet there. I've been there.
So yeah, I just have like, I'm gonna go. Yeah, like it's like yeah, like these are kind of like the resources I've used thus far. So like I was looking at this like chosen way. I follow Phoronix. I'm on the Mesa mailing list actually. I think I can like show you looking. But like yeah, here I'm like I follow the mailing list. This is the MR I was talking about actually. Yeah. So TLDR, what I did is that I just kind of like got it and like turned in like all like sanitizers and static analysis things that I can find, and I'm like, oh, okay, what's some bugs or like something that I can fix. And turned out, and like something like the SPID Radeon, right? What turned out is that when getting plane info in DRM and the DRM driver, there was an error, there was a return code that wasn't being checked. So like if it had failed, it would have just continued on like nothing had happened. Yeah. So I ended up actually adding those error checks. So that was like my first contribution. Yeah. Here, let me scan you. Yeah, I've been showing a lot of people today. Yeah. But yeah, I'm hoping to like space also get like some help because this is all like not trivial, and I just need people to like love. Is this okay? Yeah, I didn't know. Oh yeah. Yeah.
I guess we can get started. Good afternoon, folks. We had a great graphics presentation like a few minutes back about how DRM system works, PVR. Now let's go a lot more deeper down. So this presentation is about OpenOCD. I know I work for Texas Instruments. We have this thing called as Code Composer Studio, but I'm not going to talk about that here. The presentation. Okay, thank you. Is that better? Kinda. All right, let me try speaking louder. Okay, so OpenOCD. Presentation is all about OpenOCD. Most of the folks who are familiar with PiOCD, OpenOCD, most of the folks have been working with microcontrollers. The world has changed quite a bit with heterogeneous systems, and we'll be talking about a lot more about what those challenges are. There's a standard solution, way of doing things, and there is our way of doing things here. So, sorry, marketing team is paying for the money for the flight, so I got to do this. TI, we love doing everything in upstream, and this entire presentation has been merged in mainline. So all the patches, you're not carrying any of the patches at all. So, and you can replicate this. We are part of a lot of foundations. Though OpenOCD doesn't have quote-unquote Linux Foundation umbrella underneath it, we do contribute quite a bit into it as well. My co-author, Jason, unfortunately he couldn't make it here due to some personal reasons. But we are both from TI. We've been with TI 20 plus years now, on an average. He's the hardware architect who's been involved with hardware debug subsystem for quite some time. I'm the software guy. And this is very typical in TI where we two work very closely to come to a solution. Anyway, so some standard disclaimers. Please don't ask on the TI support forum, what is OpenOCD, why did Nishan say this, don't get me in trouble, please. So the standard disclaimers that come out. None of this presentation is an official strategy statement from TI. It is just my personal pet project that is running around. I know many of our systems do have DSPs in them, C7, C6, AI engines in them. I know theoretically it is possible to make it work with OpenOCD, but we are not going to cover them. We're going to stick purely with ARM. It's easier to discuss. The last one, unfortunately, I've been debating quite a bit. How simple do we go in the presentation? How complex do we go? So the depth is very subjective. If you look at the schedule, I did put some intro videos in that I had done for the rest of the team. That might be a good way to get started if you're not comfortable with OpenOCD whatsoever. Like if you have not worked on JTAG, that'll be a great place to get started with. I'm not going to go too deep into the basics. I'll start stepping into the middle there, but I will not go too deep into OpenOCD either. So it's kind of somewhere in the middle. We'll touch on a little bit of introduction, what this thing is all about, what documentation should you read to understand a little more deeper, what videos you can watch, understand the key concepts a little bit. But I'll try to avoid going deep here, okay? The real talk is about how to make OpenOCD work in heterogeneous systems, and I'm going to focus on that. Okay? But please feel free to ask questions. Stop me at any time and clarify if you need. But there's quite a bunch of data that we need to share around. All right, so why? I love the standard answer because I can. For folks who have used Raspberry Pi inside a case, having to open the case up, plug in JTAG just so that you can start doing debugging is not a pleasant experience. So I like to sit on my couch. I like to work my stuff from my couch. And more importantly, when microcontrollers started becoming a realm of open source development, like when Zephyr started getting in our interest area, one of the core questions I had was, why can't I do Zephyr programming like how application developers do? You know, GCC A.C, GDB A.out, and hey, I'm debugging stuff. Why doesn't it work that way? Why do I need this fancy hardware to do stuff? So we were thinking about it, Jason and I, we threw some ideas around. And then within TI, we have this hackathon that we do once a year. It's a 24-hour stress cycle for us, but they let us do anything we like to do. So we're like, hey, let's go and do this. And we made it happen back in 22. It took us a year to get it upstream, but that's how this project all came together. The idea is to make microcontrollers no different from any other subsystem that you're developing on. So if you're doing bare metal programming or you're working with FreeRTOS, for example, or Zephyr, you should be able to build it on the target, deploy it, get your debug, cycle all over again. And you don't need any specialized hardware for doing it. Now, there are constraints, of course. We'll talk through the constraints, but that's the intent here. Now, I know my friends in other SoC vendor, SoC companies also have these capabilities to different levels, but keep in mind, not everybody is equal. So this experience might be very unique to TI, or it may be possible on, let's say, NXP or ST systems too. Just a heads up. I've not tried them, so let me know if it works. All right. So some basics as such. What is heterogeneous processors? This is a scary picture for people who are used to microcontrollers. I'm sorry. I didn't mean to give you nightmares here. This is TDF4 VM. The TI product numbers are crazy, but this is one of our Beagle-born AI64, if you guys are familiar with that. This is the chip that is on it. It's got like gazillion R5s on it, M4s, A72s, all working in conjunction in a single system. The traditional way of working in this environment is typically you would use Code Composer Studio. Oh, there are DSPs too, I forgot to mention that. But I will not talk about DSPs, promise. The traditional way of working in these systems is, if you're Linux, there's a Linux way of development, right? You use, whatever, Yocto, Debian, whatever your poison of choice of distribution. And then there is this black hole world of RTOS development. They love their JTAG. I'm yet to see an RTOS developer who doesn't have JTAG on his desk. But I'm yet to see a Linux developer who has JTAG on his desk too. As most of my Linux colleagues keep on telling me, Nishant, not everybody likes JTAG. But try doing that when your DDR is not working. That'll be hard to get a printf out. Anyway, there are 3 different types of processors on this SoC. Cortex-A's, which is your big application processors. Cortex-R's, which is your real-time microcontroller. For the people who are involved with FUSA, functional safety thingy, these Cortex-R's can run as lockstep processors, so 2 processors running together. And then you have your Cortex-M, which is a power-efficient microcontroller doing the little things on the side. This entire coordination of multiple things talking among themselves, it's like an orchestra. It's actually a magic when you see this thing actually working. If you come out to a TI demo, there are a few demos that we showcase how this thing actually works. And we work with the OpenAM community to actually standardize the interfaces so that we, from TI, are not unique. Xilinx, AMD, NXP, ST, all of us are working together to standardize this communication interface. Why do you need heterogeneous systems? Because the old story of one single processor architecture trying to do everything simultaneously is not economical. You can't get your power numbers proper, you can't get your performance, and you can't get everything done in a single processor either. This is the wave of the future. Everybody who has tried to fight this ended up here in one way or the other. Look at your AI engines. Gosh, everybody likes NVIDIA nowadays, don't you? You don't look for an ARM processor that does GPU along with the processor anymore. Anyway, JTAG by itself, it stands for Joint Test Action Group, which is not a cool terminology, but it is like any electrical engineer, any embedded guy knows this stuff in the back end. It's a daisy chain bit flow. So you inject 1010 down the input, you get output, and there's a parallel clock that runs along it. And you can talk to different, what we call as test access points. And tap is your interface into the processor. There's a beautiful part 2. I wish he finished his part 3, but so far part 2, article on Medium by Alexander that actually talks through how this works, how does it physically work. And he gives you some beautiful diagrams to explain this. Again, from my perspective, I think it's a little too basic, but from our thought process, think if you have to work with hardware debugging on a microcontroller which does not yet have a firmware loaded on it, your step number 1 is to start talking to the processor, right, before you can see what has gone on. That is only possible with JTAG. It's very fundamental in our system. Core site is another terminology you will hear. If Matthew Poiter was around, he's not around. He's like the demigod of core site support in Linux kernel. He's been doing that for quite some time. Nowadays, he works on remote proc. But core site is essentially the debug architecture ARM evolved to over the number of years to standardize how do you talk to a processor. There are certain registers that are involved, but it uses the same standard JTAG terminology. How do you lockstep? How do you stop a processor? How do you set a breakpoint? How do you set a watch point? There's standardization for it. In fact, you have Linux kernel also supporting that too. Like when you enable KGDB, there's stuff in the backend that can enable this for you. Again, there's a lot more documentation around it. There's a specification called ARM Debug Interface version 5, which would be very interesting to read as well. Now we come to the fun stuff. OpenOCD, my favorite topic. It's a very exciting group of bunch of people here, very typical open source community of characters, and OpenOCD has its characters. They just love electrical signaling. It's an in-circuit debugger, which allows you to get inside the processor and start debugging any processor that you want. If you were a security guy, this is your nightmare tool. You want to block this guy from ever talking to your processors. Now, if you're a guy who wants to learn stuff, this is your friend. And I look at OpenOCD as my friend. How to use OpenOCD and what is OpenOCD in the basic form. I put a couple of videos on YouTube that I had given a talk a little earlier about. But in a nutshell, it's an app which kind of looks like this. I'm sorry, that's an ugly picture of a board. And you can see there's a lot of wires that I need to pull between 2 different components. You see, I'm a lazy guy. I don't like going and plugging stuff in. But overall, you would have any idea of your choice. You like VI, you like Emacs, you like VS Code, pick your poison, right? They all talk GDB. So use standard GDB, GDB multi-arch, whatever you like. And then GDB talks to OpenOCD using network socket, some port that you want to get it to talk to. The traditional way of running OpenOCD is to run OpenOCD on your PC, and this OpenOCD talks over USB to a dongle of some sort. Thumpa stands for, anyway, forget it. The Thumpa is one of the dongles that are possible. TI also enables something called XDS 110, both of which are supported natively in OpenOCD. Now, if you folks are familiar with Sega tools, right? They have good support on OpenOCD too. So it doesn't matter what tool you're using, they all talk JTAG. The big difference between these are if you're using FTDI bit bagging, well, your speeds are in the tens of megahertz. But if you use a faster, more expensive dongles from Sega, you might hit megahertz range. That'll be the big difference that you'll see. But that's typically when people say JTAG, this is the picture that they have in their mind. Now, you can replace this stuff on top. Have folks heard Lauterbach here? At least, oh yes, 2 people. Yes, good. Lauterbach, the ARM DS5, all these tools essentially come. This is the view that you work with. You can replace that entirely with Lauterbach or ARM DS5. This stuff that you see in bottom essentially remains the same. Internally, there is what we call as a debug subsystem. We'll go into a little more detail of how that works down the slides, which routes the communication to either Cortex-A or Cortex-R down. This is a very simplistic view of how this entire scheme works. As you start drilling down, you might need a bottle of aspirin, but we'll get there. All right. Any questions so far? For folks who are not familiar with debug, I know there's a lot of questions. But folks with JTAG, any questions with OpenOCD? Okay, let's go in a little more. What I don't like is the fact that I have to use my PC, I have to use hardware dongles, and if you look at this little picture over here, this cable is what they call as a tag connect cable. Okay, this is Beagle AI64. The way that they reduced the production cost for the board was to reduce the number of connectors on it. So they're using a pogo pin that plugs onto the PCB. So all you need to do is put the test point in a certain way, and boom, you have JTAG connectivity. It's great, except for one little detail. The cost of this stuff is close to $100. I don't want to pay $100 for debugging a $200 board. That's 50% of my board cost right there. I don't want to do that. Plus, I have to physically move my body, plug the cable in, and actually use it for doing my stuff. So we don't want anything physical in this picture. And that's where we start using memory. So there's quite a bit of benefits out of this thing in the approach that we took. When you're talking electrical signals, you are slave to what electrical routing you can get out of the system, what rate of bit bagging you can do with FTDI. What if you were to remove all of that? You could talk at processor speed, at bus speed. Your debug is like super fast. And that's what we ended up seeing. And we didn't anticipate it initially. I mean, we were not thinking that this thing is going to be beautiful. Like, what's going on? This is so fast. I'm like, oh, that's why. You also can get to debug remote cores, all the R5s, and if we need, we can get to DSPs if you want to. But in this solution, what we have done, yes, you need to run OpenOCD somewhere. We run it on the A53 within the SoC itself. So you're running OpenOCD on A53 using the SoC bus to communicate to the debug subsystem, and then using that to control the R5s. That's the nutshell of this entire story. How we do is a little more interesting detail. But the good part of that is, once you run OpenOCD, guess what? You can run VS Code on the target if you like, or you can run VS Code on your desktop. It doesn't know the difference, because it's all network sockets at that point. You can run SMP. You can enable RTOS awareness. Everything works seamlessly out of the box. So, yes, let's talk about negatives. We being lazy, we decided to use /devmem. And I remember there were experiences of production devices that exposed devmem, which was not pretty, so I'm sorry. But we couldn't think of anything better or easier to use. /devmem was very easy. But if you are rolling your own distributions, you can probably control this, the kernel.config, which allows devmem, and you disable the strict devmem access. But if you are using something like a production OS, like let's say Red Hat, CentOS, for example, they're very, very strict about this stuff. They actually lock these down, and you will probably not have access to it. But if you're using Yocto, most of the Debian distribution, you're probably okay. If you can roll out your own kernel, you are still okay, because you can enable this on your own. This is kind of a little bit of a gotcha though, and the other gotcha is that I'm assuming none of you guys are using root to work on your board? I think you are. Okay. If you are using root, please don't. Please use sudo to get when you want to. So you need to be in the sudo user to be able to actually run OpenOCD and get to the devmem. The actual build of OpenOCD is straightforward. These are standard build. You just run .bootstrap. There's a bunch of Git modules that it starts dragging in, run .configure. The big stuff is enable daemon. So we debated it a little bit on Gerrit. They do their reviews in Gerrit. It still exists. And the thought was that daemon doesn't make sense for 99% of the platforms. Maybe TI platforms, and maybe a few people beyond TI might start using it. So it has to be explicitly enabled, and most of the standard distributions you'll get out of either Debian or any of the folks will probably not have this enabled by default. So just a heads up on it. And then you do a make install, and you're usually done. One interesting thing that you want to keep in mind is that unlike building OpenOCD on PC, most of you folks are probably embedded developers, which means you probably use Yocto, I hope. Yes. You may have to customize your recipe a little bit. So you can, wrong key, go back up. There we go. I've kind of given a hint how to build it for Yocto with the extension. So you can use your package config, dmem, -- enable dmem, and do a plus equal to dmem. Meta OE recipe is your reference. So you can do a bb append to extend that further. And you can kind of roll out your own distro with dmem enabled OpenOCD. It's not too hard for folks who are a little comfortable with recipes. But if you're not, use Debian, .configure, make, you're good to go. You get the same thing. So once you start OpenOCD up, this is how the log looks like. And this is what a heterogeneous system looks like. I took a different processor for this example. We took an example. This is actually the simplest processor in TI's K3 family. We just have 4 A53s and an R5 and an M4. Most of our other processors have much more complexity in the system. So A53s are running in SMP mode. They're running Linux. R5 is running FreeRTOS, and Zephyr is running on M4, in my case. So when you run with this configuration, SWT native, so we kind of emulated single wire debug and called it native. So it's actually, if you're technically correct, this is very wrong. Because there's no physical single wire debug coming into play at all. Okay, but that's the term that we kind of overrode, and we kind of hacked around that path. It was the easiest way through. So this configuration file is available upstream within OpenOCD. So if you run this command, you'll see these ports open up. Each of these ports directly talk to a processor. Now there's a configuration that you can do where all these processors are grouped together in SMP configuration. There's a hardware thread concept in OpenOCD that allows you to do that. For our interest, we are talking GPMCU, which is the M4. And if you connect to port 339, you get to here. You can start loading your Zephyr images. You can start debugging it. So this is interesting because the moment this port is opened up, Rust starts to behave nicely. Zephyr starts to behave nicely because you can do West build, West test. If you're using cargo run starts working. Everything seems seamless, as if you're running a native application. It was surprising. I mean, it's pretty cool to see it work. And if any of you guys want to actually see the demo, I have it at my booth. We can come along. I can show you how it works out. Little more complex setup, right? Now you add networking access. So I don't want to actually, my ID, I want on my laptop. The board is sitting here. It's connected on Wi-Fi, but I want to debug it from my desktop, or my laptop sitting around. So you can enable, and please be careful. If you're on home network, this is probably fine, but if you're on Starbucks network, this is probably not good. I kind of opened it up to all the ports, so please do a SSH tunnel next time if you want to do it. But this is the cheapest of all. Just open up the port up. It connects to all interfaces. Just connect to the IP, and you're good to go. This is a little custom stuff. Set RTOS variable. There, I'm saying that this processor is Zephyr. So it has now Zephyr awareness available for that processor. I can do a combination. I can run FreeRTOS and Zephyr simultaneously. So FreeRTOS running on R5, Zephyr running on M4. Using the same variable, it's an array, essentially, named array. Saying that GPMCU is running Zephyr, main R5 is running FreeRTOS, and use the same configuration. There's different ways to skin this thing. One thing I would not suggest to do is, since you're running this on A53, please don't use this to debug A53. It's not going to end well, okay? Because you're going to stop OpenOCD debugging. I mean, you get the circular loop coming in. The actual GDB command itself is GDB multi-arch. It uses XML to communicate with OpenOCD to go and figure out, hey, what kind of processor are you using? Right? Are you ARM64? Are you ARM v7? Whatever, right? RISC-V. By talking to the port, it automatically talks in the backend. Now, this is very trivial implementation. I mean, this is like bare metal development stuff. Most of you folks who are going to work on Zephyr will probably wrap this under your WEST commands, right? WEST does have OpenOCD communication because that's what microcontroller guys do. And they try to use that from your PC perspective. But you no longer need a PC for development. You can run this from A53. If you're using Rust, you would wrap this under cargo. Again, there are some cargo files that I'll show along as well. Anyway, so if you don't know which operating system you're working on, which is maybe, there is an option for you to say, auto, go figure it out. OpenOCD is smart enough to do that too. All right, here's a screenshot that is hardly going to be visible. I have this thing with black. I don't know why. Oh, crap. I didn't think it was this bad. Oops, I was supposed to say that. Anyway, so this is the code. This is the actual driver code. What I have here is a GDB dashboard, actually debugging M4F. On this side, I have OpenOCD running. This is just debugging one processor, okay? And then I have Lauterbach IDE, okay? The guy who needs the specialized hardware, but he also knows how to talk GDB. So this could have been DDD, VS Code, anything of my choice. So this is debugging the M4. So you have two different debuggers running simultaneously with no JTAG hardware. I'm actually debugging this sitting on the side on the M4 with Zephyr in this. Was it Zephyr? I think it's Zephyr. This was bare metal code that I was running over here. Let's make it a little more interesting. Rust, of course. Let's forget about the little CVE episode we had a few weeks back. I was learning Rust, so the code is like really bad. But here's an example of cargo run actually working. So you can run stuff on, so I'm running cargo on A53 here, and OpenOCD is connected on a second terminal, two SSH terminals. And guess what? The guy is sitting and debugging code on M4. It doesn't even appear that I'm sitting and running a microcontroller. I feel that I'm running a native app at this point. This is how I feel I should develop. I don't want this special magic stuff to do. And it's pretty fast, which is, I like to iterate. I'm not a designer per se. I don't like designing everything and then running things, make a lot of mistakes and get to the perfect solution. This kind of works for me. Okay, so some things that you have to be careful. Now this is generic stuff that we have to be careful about anyway. If you are on heterogeneous system, you have to be careful about watchdogs because, hey, we are hardware. We like watchdogs. If you don't pet the watchdog, it's going to come and bite you. There are different techniques on K3 architecture how to prevent the watchdog from biting you. If you're writing serious firmware, you probably are playing with watchdogs. But initial days, stay off watchdog. Some standard stuff, like you just made this change, you're reloading and rerunning. You expect the register to be 0x1 set, but you end up with 0x3 because in the last run you set 2, this time you're adding 1 on top of it. Few other TI specific problems that we have a device manager because the system is so complex, and you can see this in most of the newer SoCs. The power management itself, there's a microcontroller doing power management. So that role is now central for everybody else who have become slave, including the A53s or A72s you have in the system. So you need to talk to that guy to get anything done. So you suddenly are talking to an IP and boom, exception. Why? Clock is not enabled. The last caveat that we have is that I consciously chose not to write TCL scripts that will directly go and bit bang into registers and enable a processor. Primarily because the reset vector is a security domain. I don't even get to see it. So you need to use TI SCI APIs or PSCI APIs or SCMI API, whatever your favorite poison is, to actually set what the reset vector of the processor is. The VBAR, reset VBAR, whatever you want to call it. I don't have direct access into that. So that has been one of my challenges, and I depend on remote proc to do that work for me, including memory carve-outs so that we don't step on each other. All right. Are you guys tired yet? All right, if not, let's get some pain in the story. That's the actual debug hardware architecture, insights. Okay. You'll see a variant of this on different SoC. Now, I've taken a very simple SoC, AM625. If I were to take a TDF4 VM, it's going to be much more complex than this. Over here is your normal interface that is coming in, the JTAG interface, and there are multiple routes into the SoC for the processor. So the one that we will be interested is this little guy, who is the R5 and the M4 over here. These are the two guys that we were showing examples of. All right. This entire story is to bypass hardware, right? So what we want is to disable this thing on the side. But we also have to be careful about the way you talk to the hardware. From OpenOCD perspective, he thinks it needs to talk to hardware. It doesn't know that I'm emulating the hardware signals coming through. So I need to plug into the right layer in OpenOCD to be able to get the calls coming in from the processor target and route it as memory accesses downstream. So there are two things that we ran into. One thing is that, like for M4, was pretty cool. I could do an access port, direct access port remapping, and it just worked. But for the R5s, I had difficulty. I had to actually emulate an access port itself. So this is how we kind of did for M4. The data path from the SoC address goes via this one to the AHP AP, and boom, you're good. You can talk to M4 all day long, no problem. No software emulation needed. Direct register read-write, you're good to go. R5 wasn't the same. We actually had to create an emulated access port, which means we act as if this hardware, or rather this APB AP exists. So we emulated an APB AP in software. Now, we are not the first to do it. This is not science that we discovered. Apparently, other people have done the same. So we cheated, we stole. So this is overall the software architecture of OpenOCD. There's a lot of dependency diagrams in terms of how the JTAG helpers work, RTOS, and target interfaces. Long story short, the SWD, there is a way to override it and kind of emulate SWD in OpenOCD, which is what we chose as a route. Time check. How am I doing? Okay, 10 more minutes, I think. All right, so internally, DMEM has two implementation. I mean, the source is available. You can look at upstream OpenOCD code. There's a little bit of Doxygen documentation around it, but hey, who needs documentation, right? So there are two memory maps that it maps out. One for direct AP access. So you have the access port as is for M4, for example. You give direct access to OpenOCD, and he's perfect. The other one that we have is emulated. For the R5s, we have to emulate an access port. So the register access, OpenOCD talks tap accesses. We translate those accesses using a state machine into actual register modes. So there's a very tiny state machine that we maintain as well. Basic configuration in OpenOCD, how to do it. I have not studied other processor architectures, so I think this should scale to other architectures too. And the reason why I'm very confident is that TI did not do anything magic with CoreSight. We have not customized it in any way. Unless your SoC vendor has customized it, this most probably might work for you too. The last one was the emulated mode itself. This is the state machine I was mentioning about. The direct AP access is straightforward. The emulation, these are the standard ADI registers that we have to emulate out. In real hardware, they are registers. They have specific offsets that you go and poke into. In our emulation mode, we act as if those registers exist. So you get a tar register offset. Based on the tar register offset, you're doing something in the backend. Straightforward stuff. There is control status word. What address do you want to transfer it to? There's data read, write. What are you actually trying to do? Then there's bank registers, 4 of them, and configuration, base address, and identification. This is the base register configuration that we have. In terms of the state that we manage, we just need to maintain 2 states. What register was it going to? So we need to remember that because the next operation is going to be based on that register offset. And what's the control status word that was asked us to do? So maintain the state of the control status and what register are we going to? With that, the code is not that complex. It's like maybe 100, 200 lines of code. It's a very straightforward state machine for it. But with that, you get MMIO emulation access as well. But the story doesn't help end, right? Again, I told you this entire thing is a pet project between Jason and me. We kind of did this in 24 hours. It took us a year to upstream, sorry. But there's a lot more we have to do, yeah. We stopped at just basic debug, but we could go and enable CTI and trace support. Something like embedded trace buffer. What is trace, right? So folks who are familiar with JTAG probably know this already. Instead of stepping through every single line of code, you set up a breakpoint, say go, and boom, you have a full trace of every single instruction that you executed till that point. What data structures were changed, you can walk back and forward. There are a lot of IDE tools that make a lot of money with that. It's possible to do that in OpenOCD as well, but nobody has invested time to enable that yet. Embedded trace module is a much more sophisticated scheme to get more in-depth trace information as well. There's something called a system trace monitor too. So your bus traffic, you guys have used perf, right? I hope you have. So you get in-depth knowledge of where the bus traffic is flowing, how much is your bandwidth utilization. What if you could see that at every fabric level, every choke point within the fabric? What is each DMA channel doing? STM gives you that visibility as well. These are things that are standard stuff, and in TI documentation, we publish everything. So, but of course, someone has to take the interest in writing, which we still haven't done. This one is my pet peeve. I don't use VS Code, honestly, but I understand there's a lot of VS Code fans. I like VI. And I respect you guys, right? So I did look a little bit into enabling VS Code, and I found that Maddox has been doing some good works with the device packs for ST. And I was like, oh, what's he doing in the backend? He's been using SVD file formats, and those are huge when I start generating for TI SOCs. So I don't want to put anything like gigabyte of files out there, which don't help. It'll be nice if you could just click and drag and drop and see the registers of how your GPU looks like without having to do memory map, dump, bit field decode manually. It's possible to do that in VS Code. I just don't know how to do it efficiently. Need some help though. The last little detail, which we've been trying to work with OpenAMP team as well, is every distribution enables different kernel modules differently. Now, folks who are familiar with device trees know that the probe order, our good friend -e probe differ, is a very good helper to make sure that your IDs are different for every boot. So what I get on Debian and Yocto tends to be different remote proc IDs. I get remote proc ID 16. On the other one, I'll get remote proc ID 4. And I'm like, oops, I have to change my makefile again. I would like to standardize it. I did post a patch which Matthew killed me for. It's aliasing for remote proc. I thought it was trivial, but apparently there's much more deeper questions around it. So need to work on that. Future directions, anybody heard UCIe stuff, chiplets, fancy words stuff? There's a lot of UCI consortium is trying to work on debug subsystem, and they are looking at when your chiplets are integrated for a full SOC, it's very dynamic in the nature. So how do you discover this entire system and still without having like hard-coded configuration files? So a lot of work happening on that. And this is probably my pet peeve. RISC-V, guys. We are not part of RISC-V International. Anything I say is my personal opinion, not my company's opinion. Remember the trade-off that I have. ARM has spent a lot of effort over the last 10, 20 years to do this right. RISC-V ecosystem is relearning all the problems all over again. It shouldn't happen. You can look at their debug specification online in RISC-V. I wish there could be some unification here. I wish we could have the same core site-like standard in RISC-V, which both ARM and RISC-V were to follow. It would help all of us. But this is going to be a very interesting journey. As RISC-V starts maturing, you already have a mature ecosystem to look up to, but you can't copy from. And this is unfortunate. For me, that's one of my saddest things that I have learned looking at this thing. All right, so trying to keep to my time. Sorry. I couldn't have done this without the community. I mean, I started this off one late night, someday, sitting around. This is how I start new projects. A lot of people in the IRC community have helped me through this. Big thanks to Antonio, Paul. Beagle community has been a big guinea pig for my team. I usually throw ideas out there, and there are a couple of guys who like to pitch in. In fact, they added J7 TDF4 VM. Kylan did. And Kevin, Fred, Tony, they have worked their magic around on AM65 and J7. Yeah, so that's us. So if you guys like the stuff that we do in the community for OpenOCD, don't buy me a beer, don't buy me a coffee, just donate in. That's more or less what my presentation was all about. In a nutshell, you do not need hardware to do JTAG. Microcontroller heterogeneous programming does not need to be hard and evil. You can use your favorite editor too. Simplifying. Questions, please. Might be out of time now. Okay, so if you guys are interested, there's like tons of backup material you guys can read through. Please go ahead.
So have you given any thought about how to debug the A53 core? Is OCD movable to a different course? I mean, heterogeneous core?
KGDB gives you that capability already. So
Okay.
nothing extra we need to do there. Now, you can also run the same OpenOCD. And again, this is theoretical. Since it's POSIX compliant, in theory, we should be able to run OpenOCD on Zephyr from R5 and debug A53.
Right. That,
in theory.
Yeah.
I never tried it yet.
It has to be compiled for it, that's all, right?
Yes,
Yeah, that's the
exactly.
mistake, right? Cool, thanks.
You mentioned the TDA for VM.
That's right.
I'm curious if you tried it on that chip, or that's just in theory it should work?
Yes, it does work.
Okay.
And I have a nice little picture. Oops, sorry. My usual ugly picture to show you that it works. This is on TDA for VM.
Awesome, thank you.
You're welcome. Oh, by the way, this is on 6.9 RC2.
Okay.
I work with mainline. Jason?
Would you do the same for the non-ARM cores and some of these SoCs like C7X? Did I miss that at the early part of the presentation?
We said we won't talk about it.
You won't talk about that?
Okay. Sorry, I'm just kidding. In theory, it is possible. I'm not going back into the disclaimer section. In theory, it is possible. But I'm going to use the same term my imagination colleague used in the previous presentation. Let's say it is dependent on the business decision at the moment. Any other questions, folks? All right. I'm available for the day, and you guys can reach me on IRC as well. There's a lot of places. I'm like a social butterfly nowadays. You can find me on Discord, on Zephyr, OpenAMP, and BeagleBoard forums. IRC, if you like, still people use IRC. If you do, we folks in OpenOCD hang out in liberator.chat. You can find us there. And if you want to reach us on Fediverse or LinkedIn, we are there. Thank you.
You're talking to here. Yeah, okay, it's on. Okay, then, I guess we'll get started. So my name is Doug Anderson. I am a software engineer on Chrome OS at Google. And today I wanted to talk to you guys about 2 tools for posting patches for upstream Linux, Pacman and B4. So before I get into them in too much detail, I'm going to tell you stuff that you already know probably, but just in case. How patches get into Linux, we basically use an email workflow, right? So you post patches to the relevant mailing lists, and you send it to the maintainers, and you figure out how to get those patches up in email. All the code review happens in email, via plain text email specifically, and then you do the code review, you get responses from maintainers and other reviewers on the list, and then it's up to you to take action on that and send a new version of your patches. And you keep doing that, sending new versions via email, getting responses via email, until everyone's happy and some maintainers land your patches. So that's the overall flow. I know there's still plans to move away from the email workflow, maybe someday. At least I could swear I heard Linus Torvalds say that, eventually even he believes we need to move away from the email workflow, but it's nowhere near happening right now, at least for the majority of the kernels. So we still have to figure out how to send patches. So the vanilla, if you just go and don't use any tools, the vanilla way that you send patches is you use git format patch to get your patch in a format that is ready to email out. And then you figure out who to send it to, probably by using the get maintainer script in the kernel. And then you use git send email, and you manually copy the result from get maintainer to the to and cc args, and maybe add a bunch of other args like maybe subject prefix or other types of things like this. So you type in a big long command line to mail out your patches. And there's all kinds of different slight tweaks to this. Someone, when they reviewed my patch or my slide, said, oh, you don't pass the subject prefix, you pass -v5, right? And so there's a bazillion different options. But suffice to say, you have to do a long, complicated command line argument. And probably everyone out there scripts or automates this in some way, and they roll their own way, because this is a pain in the butt. So the problems here is, like I just said, you've got to manually run get maintainer and send that to git send email. And every time you send the next version of the patches, remember I said you got to iterate over, so every time you send the next version, you have to again construct that big long command line and get everything right. And it's easy to make stupid little mistakes and mess up, and then you kind of look a little foolish. It happens to everyone, but it's better not to. And of course, if you're sending a big long series of patches, you're expected to send a cover letter with it. And usually you kind of have to keep track of that yourself somewhere, or maybe you use the git branch description to store your cover letter, and there's some help there for it. But it's a little awkward. So, and I guess the last thing here is that, sending patches, you need an SMTP server, which is not a terrible problem, but tends to be a problem for a lot of corp users. So if you work at random Chinese company, they may, or actually maybe even random American company, they may not give you an SMTP server to send your patches from. So that can also be a problem here. So the first tool I want to talk about is Pacman. So I've actually been, and of course I put a gratuitous picture in here. I just went to some generative AI and said, Patman sounds like I thought a superhero that solved crimes by patting people on the head. And so it kind of seemed like this like goofy little superhero would maybe be like a right emblem for him. But anyway, you can laugh at him. But Patman's been around for a long time. I've actually been meaning to give a talk on Patman probably for the last 5 or 6 years and never got around to it. And back at that time, Patman was the only tool like this. Since then, B4 has come along. And so what used to be my vision to give a Patman talk became a Patman and B4 talk, and comparing and contrasting them. So we'll see how it goes. But I do have, I'll admit, a slight bias because I've been using Patman for so long that I like using it, and it's my workflow. And so I apologize for any bias. It was written by Simon Glass. Simon Glass has contributed some to the Linux kernel, but a lot more to U-boot. And in fact, Patman lives in the U-boot Git repository. So it's a U-boot tool, and it's widely used in U-boot as far as I understand. And even though it's part of U-boot, it's actually incredibly useful for Linux as well. So it has specific Linux support in it. We landed extra Linux default options that were more appropriate for Linux back in 2013. So this is a 12-year-old tool that's explicitly had Linux support for the last 11 years. So quite a long time. But despite that, almost no one uses it in the Linux community. And the last thing I'll mention is that one of the earliest criticisms I actually heard about Patman was that it was too easy, which is really kind of funny. And it is too easy a little bit, right? So there's, if any of you went to Dimitri's amazing talk just before this, he said, hey, don't spam new versions out all the time, and don't just kind of like cram 30 patch series out into the list and things like that. Patman makes it, and so does B4 actually, but Patman and B4 both make it really easy to just, oh, let me make my changes and send it again, and you don't have to go construct that long command line argument. And therefore, it's really easy to spam new versions of your patch. And so that was kind of an early criticism in Patman, but also it was early praise too, right? Because it made it so easy. So Patman's main features are basically just to avoid you having to do the git format patch and git send email and construct all of that yourself. And so it does what a lot of people were already scripting themselves, but in a standardized way. And one of Patman's really nice things is that it helps you keep track of version history for each patch. And we'll see how this looks later. But every patch, you kind of keep track yourself of what you changed in each version. And then as you send future versions, all the previous version history is maintained and then formatted really nicely. And when you first say, you're like, how could it help you, right? And you'll see as I go through some examples of what patches look like this. Patman will also, by default, automate calling checkpatch for you. So it helps you not forget to call checkpatch. And actually, if you have a long-ish patch series, it can be faster because Simon, I think a year ago, added parallelization to this. So it'll call checkpatch and get maintainers for all your patches in parallel. And then it will serialize and give you the results. So you don't have to wait quite as long. One of the things that Patman's features that I actually like the most is one of its earliest ones, which is to strip downstreamisms from patches. And so I don't care so much. It was originated, Simon was on the Chrome OS team when he wrote it. And so he takes out a bunch of Chrome OS things that happen to be in patches and strips them automatically so you don't accidentally send patches with them. And I don't care much about the bug equals and test equals. Those are weird Chrome OS lines. But what I really like is that it strips out the change ID from a patch. So I happen to develop my upstream and downstream in the same kernel tree. And so when I want to build upstream Linux, I just, in the same kernel tree, check out upstream Linux, build it and put it on my device. And then I want to test downstream. And without doing anything different, I check out downstream and build it and put it on my device. And so what that means is that in my kernel directory, I have those Garrett hooks that every time you touch anything, adds change ID. And So if I use B4, I have to manually remember to strip that change ID out every time. With PatMan, I don't have to remember. It just takes it out automatically. And so I think most people that use B4 have a separate kernel tree just for running B4, and they maybe do their testing in that separate kernel tree, or they maybe do all of their upstream development work in that kernel tree. But that's not how I work. So. Oh, also, I guess I should mention, you can also grab tags kind of like B4 can do as well. B4 does a better job of it because it interacts with lore. But PatMan can also grab your reviewed by and tested by tags automatically from a patchwork server. So it's not from lore, and unfortunately, we don't actually have patchwork servers for most of LKML anymore. So it's of limited use in the kernel, but it has that feature. So the basic premise behind PatMan is that you actually edit the patches themselves, and you put special annotation tags in the patches. And then when you use PatMan to send the patches upstream, it uses those tags to get its metadata and then strips them out of the patch for you. And it uses these extra tags that you add to know what to send to get send email, what to do for a subject prefix, and how to generate version history. So what that looks like is here. So this is a patch that I sent out, and it's, this is what my commit message on the patch looks like. It has the subject line, all the details about the patch, and then just in the commit text, a bunch of tags. And so I have the tags series version 2. It means that my whole series is at v2. Series changes 2 and some changes. That means that this patch had these changes at version 2. And then series 2 and series CC says CC and send to the patch series to these people. And then, of course, I kind of nominally put change ID as a PatMan tag, even though it really isn't, because PatMan not only strips the change ID, but it actually uses the change ID and encodes it into the message ID in sort of a weird way that I'll talk about in a bit. So this is what that same patch that I just annotated looks like when I send it up. And so you can see it got to all the right people because of my series 2 and series CC. You can see that it got a nice subject line, patch v2, right? You can see that it got a message ID that is this long, wonky thing that all it's really doing is it's putting a unique thing here, the date and time, patch version, patch number in the series, and then the giant change ID that my Garrett hook generated for me. The reason I originally did that is that it can help with some automation in figuring out that V2 is a newer version of V1. And if you're looking on the mailing list, you can actually figure out that 2 patches are related to each other because they had the same change ID thing here. The same way Garrett uses this when you upload a new version of a patch to Garrett, and it replaces the old version. So it's the same concept, and it could be useful, except not that many people use it. So. And then you can also see that PatMan generated, after the cut, a nice version history for me. And so, kind of nice. Version history is after the cut, patch versions in the subject. And one other thing I'll mention here is that PatMan, by default, will call getMaintainer for you. And so I'll talk about B4 more in a bit, but in B4, you can have it call getMaintainer, and it will then use that to populate your 2 and CC lists. PatMan you can put 2s and CCs if you want to, but in addition to that, PatMan will call getMaintainer on each patch and send that patch to anyone who getMaintainer fingers. You can turn that off, but that's the default. And I talked about here, the change ID stuff that I already kind of mentioned. So why bother? So I just showed you, hey, you can pass all these things to get send email, but you can also put the exact same information in your commit message. So you're kind of doing the same thing in 2 ways. Why specify it one way versus the other? What's the advantage? And mostly it's for when you send V2, V3, V4, V5, V6, V7, is that you don't have to keep on listing all the people you want to send it to and keep on listing other types of things like that. And so it becomes much more helpful as you go on. But even for V1, it helps give you something that's a little bit more formatted and a little bit more standardized. So people that are new often don't really realize how they should format version history. And so they kind of format it maybe in a little bit of an ugly or non-standard way. And sometimes maintainers grumble at people for that. Here you get something that at least is known not to piss off too many people. And the other thing I'll say here is that it automates calling check patch, which I find helpful, right? Like any step that I have to do manually to remember to call check patch is something I'm probably going to forget sometime. And then someone will go yell at me that I did something stupid. So Patman, I showed you so far just Patman dealing with one patch. Patman can also deal with a series of patches, obviously. And so here's some example series, and I'll go through some of the patches, how I annotated them here. So the top patch, which is the last patch in the series, you can see I have a new tag I've never shown so far before, which is commit notes. So commit notes is a tag that says, for this patch, put this information after the cut. So it's kind of like extra notes you want for the patch that shouldn't be part of the patch description, but you just kind of want to let people know about it. And so commit notes actually shows up right before the version history does when it formats the final patch. And then you can see series version, series changes, more series changes. As you can see here, I have an example where I'm saying the overall version of the series here is 5. And on this particular patch, these things changed in V5, and these things changed in V4. And so it will then take that and give you a nice version history out of it. You can also see in this annotation, I have my cover letter. And this cover letter, the first line becomes the subject of your cover letter, and all the rest of the lines become the body text of your cover letter. So what's really weird here, right? I sort of glossed over this a little bit, but probably if you're looking at it, something maybe seems a little odd. And that's that some of the tags in Patman apply to the whole series, and some of the tags in Patman apply only to one specific commit, right? So if I look at these different tags here, series version says, all of the patches in this series are V5. You can't have a series that has like some of the patches are at V4 and some are at V3. That doesn't make sense. So the series version applies to the whole series. Series changes probably should have been called commit changes, right? Like it would be actually an interesting thing is to change it to call it commit changes because it applies only to the given commit. And so this says this particular commit had these changes at V5. This particular commit had these changes at V5. Series 2 and Series CC applies to the whole series. Cover letter applies to the whole series. And so you get sort of this weird mix of things. You get used to it after a while, but when you first look at it, you're like, what the hell? Like, how is it all mixed up, and why are things strange like this? You can see the result. Oh, go ahead, question. You might have to grab a mic from the back. I don't think we've got the mic. You might have to go grab it. Or I can just repeat your question.
Check. Okay. The question, does it resolve any inconsistencies if you have something applying to a series in one place and in another if you have across multiple commits?
Sure, so that's a good question. So what it does is it'll actually just give an error. So you can, anything that tag that applies to the whole series, if you can put it in any patch in the series. So you can put your cover letter in the top patch, the bottom patch, a middle patch, but if you specify cover letter more than once, Patman will yell at you, and it just won't let you send the patch series. And so then you have to go delete it yourself. It doesn't try to like do anything fancy like merging. Some tags like Series 2 and Series CC, those ones will be combined. And so it just, anything that is a tag that applies to the whole series, it just concatenates them all at once. And for anything that can be specified more than once, it's all of them. And otherwise, go ahead.
Do you have any example of output for series changes? Like when you have 10 patches and each has different series changes, how does the output look like?
Yeah, I'll go through some of that. So
awesome.
Actually, in this case, This exactly one that we're looking at, I've actually added this one. Some of the patches were new for v5, and so I added specifically for some of the patches. Here's the whole series, and some of the patches I added a series changes 5, and this is what I wrote in it: is run the unload routine if we have errors during probe new for v5. I added that specifically to that patch as series changes 5. The cover letter gets the union of all of the changes from all the patches. And then we will get to we'll get to more of the patches. You'll see more examples, and if it's not clear at the end, you can ask. So the cover letter is the union of everything here. And then the changes is a union of all the changes for all the patches for all the versions. So you'll see all of the patches changes listed here for v5. And then ... here's all the changes for all the patches that said something about v2. And then that's pretty much it for the cover letter. And then the actual top patch, you can see the top patch was patch 8 because the top one's the last one. And then you can see here's my commit notes, the after the cut commit notes, and then followed by the changes for this particular patch that happened in v5. And then I didn't follow anymore, didn't show anymore in this particular case, but we'll look at some more patches too. So this was what the second patch in this series looked like annotated. So this is like, if I did a git log and I was looking at the description, this is exactly what I would see locally, right? And on this particular patch, what's unique about it is it only has series changes 2. The whole series version was 5. This patch was 2. But you can see, and I gave this description for it. What changed in v2? Well, I added this patch in v2. It was brand new. So I just added that as kind of a default placeholder. And I'll talk more about that in a minute. But then when you see what showed up on lore.kernel.org, you can see changes in v2 was this. And then Patman will add in there automatically for me, no changes since v2. So that's actually why I got in the habit of the first time I add a patch to a series, I will manually add this patch is new for the given series, because after that, it will, if I didn't have this, it would have said no changes since v1 automatically, even though it was introduced in v2. So there's a little bit of weird confusion there, but probably something we could fix in Patman. I just never have gotten around to it. And this is actually that example where I have no Patman tags. In the top patch in this series, I had no tags because it was there since v1 and it hadn't changed since v1. And so when I sent it, it correctly tells me no changes since v1. So I already kind of talked about most of this stuff. Some of the tags apply to all, some apply to just others. You can actually just, if you have Patman, you can type patman -- full help, and it gives you the whole docs that talk about what all the tags are and what they apply to. And as I said, the bottom patch had no tags, and that's fine. I did say that the cover letter had the union of all of the version history of all the patches. That can sometimes get confusing, actually, because one, if you make the same change to more than one patch, then it'll be listed more than one time in that cover letter. You can solve that assuming that your version histories are all one line long by adding a series process log sort unique. It will then sort and uniqueify all of the version history in the cover letter. So that can be handy. But you also, you kind of do have to keep in mind that your version history is going to get put in that cover letter too. And yeah, I put in like the couple random feature requests, like, hey, it would be cool if there was a, commit introduced in V, and then you could just say it was introduced in v2, and then it could just do all of this stuff for you, right? Like, this patch is new since v2 or something. That would be cool. Maybe one day we'll add that. I'm not going to spend too much time on this, but you can use Patman to collect tags like reviewed by, act by, tested by. You have to do some more complicated things because it uses patchwork, and there's a lot of different patchwork servers out there, so you have to go in and add your patchwork URL. And then also, you can't necessarily easily query to find out what the series ID was that your series got assigned in patchwork. So every time you send it, you got to go find your series ID and add it to the patch as an annotation. So it's useful if you have really long series and you get lots of tags, but I tend not to use it. Also, when I run it, I use Git work trees in my repo, and Patman doesn't seem to like it. So, but I was at least showing you here. I did set it up and get it briefly working. You could say Patman status on my series, and it would tell me all the tags that showed up on the patchwork server, and then I could use -D to write them to a new branch. It will, when it collects tags, it doesn't just modify your patches. It creates a new branch and then picks all of your patches to the branch and then adds the tags to it. So that way it couldn't possibly screw anything up about your original patch series. I already talked about the little bit that Patman calls getMaintainer on everything, and it calls it on individual patches in your series. So every patch gets getMaintainer called on that patch, and the people getMaintainer fingers for that patch get CC'd on that patch. And so this is a good bad thing. So if you've ever, I've certainly gotten yelled at before by people that say, hey, you sent me a series, but you only CC'd me on patch 2. I'm not going to look at your patch until you CC me on the whole series, because you can't get context with just seeing patch 2 in the series when maybe all the context was provided in patch 1. And so some maintainers will get mad at that. I guess maybe especially maintainers that want to work offline in email and they can't just go to lore and go look up your series. So you do tend to get that sometimes. But it also is a good thing because I've certainly received patch series where it's a 30 patch long series cleaning up the same thing in 30 different drivers. And I really don't want to be CC'd on all 29 drivers that are not my driver, right? I just want to see the one that I care about. So in that case, Patman's behavior is totally the right thing. It would be nice if there was, maybe the default should be to CC everyone, and maybe there should be a flag for it. But right now, if you want to CC everyone on your series, you have to manually process getMaintainer and add them as series CCs. I also mentioned down here you can use subject. Patman has another feature for CCing people based on subject line, but it's more in U-boot. I also will say, originally I said the problem with the email workflow is you need an SMTP server. Patman doesn't solve this. You totally still need an SMTP server, and it doesn't help you there. I also do mention that if you're looking for an SMTP server and you're brand new to Linux development, and you think, I'll just open a Gmail account and use that SMTP server, it's probably not a good idea unless you're sending it. If you're using Gmail, your Git authorship, the email address associated with Git, has to match your Gmail account, because Gmail will silently, as you send it, rewrite whatever your from address is with whatever your Gmail account is. And so if you just think that you can log in with Gmail and use it as your SMTP server, your from address won't match your signed off by address, and then everyone will yell at you for it. So if you're going to use Gmail, you need to use that actual Gmail to send your patches. And I guess the last thing here is a feature I kind of like about Patman is when you call it, it will do all the formatting of your patches for you and give you one last chance to review them. It opens them all up in your editor, and you can cycle through them in your editor and check out the patches one last time before you send. So it's something I like about it. So last chance for questions. I'll move to B4, and then we can talk at the end. If anyone has any, did your stuff get addressed for how the series looked? Good. Okay. So I had to do an obligatory generative AI for B4 as well. I went a little bit dystopian here, because I figured that if Patman was the superhero that solves crimes by patting people on the head, B4 was the superhero that solves crimes before they happened. And so, it's a little evil, right? Because can you get arrested for something you haven't done yet? But anyway, sci-fi. Yes, exactly. And so B4 is a tool from kernel.org, written by Konstantin. I'm not going to pronounce his last name. I'm sorry, Konstantin. And he's the maintainer. And so some of what I'm talking about is duplicated in a video that Konstantin did when he first introduced B4 for sending patches. And so I have a link to it here. I did find it slightly amusing that it ended in part 1, and then I went looking for part 2 and couldn't find it. But, what's that? Oh, I should have looked for part 0. Oh, you're right. OK. So B4 is actually, it's a number of tools. So B4 can send patches as of recently, but B4 actually also has tools for grabbing patches from the mailing list, and it has a whole bunch of other maintainer-friendly tools for sending thank yous to patches that got applied, and a whole pile of stuff. So B4 is an amazing tool. I still use Patman at the moment to send patches, but I still use B4 occasionally to apply patches because it's so easy and awesome. So, and as I said, B4 is pretty new, but it's gotten a lot of adoption from the community because it's from kernel.org and kind of got a lot of word of mouth at conferences like this. Like I said, Dimitri just had a talk about sending patches and espoused the virtues of B4 to everyone. And that's great because it's a great tool. But it got popularity, whereas Patman didn't. So B4 kind of has a lot of the same features as Patman. It actually has an extra feature where you don't need the SMTP server. It can send patches straight through Lore's public inbox interface, and it has a whole method for establishing your identity and getting keys and things like that. And I'll go through that next. It can also call getMaintainer for you. But it does it in a very different way. It has a different idea of how that should be done. It can grab reviewed by and tested by type tags in an actually much better way than Patman does. Because it goes to Lore, and so it knows where the previous versions were, and without you having to tell it. And also, Lore just has all messages, right? So it just works flawlessly. It also does create a prettier message ID, kind of like Patman does with change ID, less unwieldy because it does it in a different way. It thinks of change ID as more associated with a series than an individual patch. And it also doesn't use that giant string that Garrett comes up with. It also does cool things like populates lore.kernel.org links, which is really nice to look for old versions because it has that tight integration with Lore. And so it knows where the old patches were. And it auto-increments the patch version, which I don't care much about, but it's a niceism. So B4's basic premise, it's the same. You're going to add some metadata, and it's going to help B4 run. In this case, you call B4 prep and give it a branch name instead of starting your branch your normal way. And then B4, like you saw in Patman, it had that slightly confusing, you stick metadata randomly throughout your patch series. And that's a little weird. B4 centralizes that, and by default, it will create an empty commit where it stores all of its metadata. And so that can be good. It's less confusing than having it sprinkled through a bunch of patches, but it also has some downsides. One of the downsides is you had to deal with a git empty commit, which Git sometimes isn't that happy about. You occasionally have to do things like, git cherry pick allow empty or something like that if you want to keep the commit moving forward, because Git likes to strip empty commits. And there's other places. B4 has a bunch of options. If you like storing the stuff in other places, you can store it in the metadata as well. But that has its own different downsides. So basically, as I said, you create this branch. It creates that empty commit for its metadata. Once you've added all of your stuff, you can call getMaintainer, and it will add 2s and CCs for you. And then you can edit the cover letter with it. That's the basic premise. I'm going to take a slight jump to talking about the SMTP stuff with not having SMTP on B4, and then we'll get back to some of the nitty-gritty details about how to format your patches with B4. So, like I said, you can get away with not having to use SMTP with B4. It's mostly useful for corp environments, but I think as talked about by Konstantin in his talk about this, is it doesn't totally get rid of a lot of the needs you might need from your corp environment. So in order to send a patch, you can now send it without SMTP. God, I can't say that today. But you still need to be able to respond and interact with the upstream community and respond in plain text email to them. And so if your company cannot support the ability for you to respond to mailing lists in plain text email, you're still going to have trouble. And so there was the question of like, how much of an intersection are there with people who can't get an SMTP server but can respond in plain text email? Maybe it's fine, but something to think about. Anyway, it's still great that it provides the option. And so I have some commands. I'm not sure I really need to go over all these because it's just all documented fairly well in B4. But you can generate a key, and you store the key in your git config, and then you ignore this part of pat@. This confused me a little bit when I followed Konstantin's instructions, which is why it's in red. Then you configure, do some more git config, tell B4 to send lore.kernel.org an authorization message so they can confirm your email address. They'll send you the email with the one-time code confirming that you can receive email, and then you tell B4, hey, here's the code I got. Ironically, when I did this to test for this talk, it ended up in my spam folder. But so check your spam folder. It gave me a little bit of a worry that if I used this method for sending mail that things might end up in maintainers' spam folders, but maybe it's just the authorization email, so hopefully. I actually talked a lot about this already. The B4 metadata, like I said, by default, it's in an empty commit. Sometimes you have to deal with that. Normally, the B4 metadata is not intended for you to go edit it manually. You can if you want to. It's just commit text. But they have tools like B4 prep edit cover, which lets you edit the cover letter. And like I said, you can say there's a B4 command for adding 2s and CCs, and there's B4 commands for incrementing version numbers manually, and all of this stuff. So anything that's in the metadata, there's a B4 command for messing with it. I will mention that, remember I said that everyone's a little confused by a Patman by sprinkling your tags everywhere throughout the commit. And that's weird, because a lot of the tags apply to the whole series. B4 actually has the exact opposite problem. So B4, by default, that empty commit, that metadata, has a cover letter in it. Well, a cover letter doesn't make sense for a single patch. So if you're sending a single patch with B4, you've got this weird thing where it says, please put your cover letter here. And it's not a cover letter. If you add text to that cover letter, it ends up after the cut for that one commit. And then the subject line of this cover letter that's not a cover letter is ignored. And so there's confusion in both ways, right? Like, no matter how you slice it, you're going to be confused sometimes. But this is essentially what the B4 empty commit looks like. You've got the tag, the cover letter subject, and tag, which is ignored if it's just one commit. You've got your cover letter text, which is your after the cut if it's just one commit. You've got your 2 and CC that automatically gets populated if you do B4 prep auto 2 CC. Like I said, very different than Patman. Patman calls get maintainer for you. Every time you type Patman send, it gets called. This one, you manually call it whenever you feel like the 2 and CC lists need to change and you need to get them again from get maintainer, and then it adds them to your cover letter. And then, of course, it was weird to me that there was a signed off by in the cover letter, but I guess it doesn't hurt. I've never had it before, and no one's ever complained, but sure. And then, of course, it shows you the metadata that you're not normally supposed to edit manually. And one thing here is you can see change ID, which is different than the Garrett change ID, different than the Patman change ID. This is sort of the B4 change ID and can be used for B4 to tell that your series is a new version of a previous series. Their change ID is at a series level, not a commit level. So they use this metadata. But you do have to be careful, because when you run B4 prep and you tell it what your local branch name is going to be, that's going to become part of this change ID. And so it will be broadcast to the world. So if you use some profanity, you're like, fix the bleeping bug, and then you send it out, it's going to show to the world that your branch name was called fix the bleeping bug, and maybe, hopefully, people won't be offended. B4 before you send things for B4, you can say B4 prep compare to the previous version. This is actually a really cool feature of B4 that you can get a diff to see how your patch series differed, so you can make sure it looks right. I often do this manually myself. I actually do a git log -- patch of all my things and like compare the git log of everything. But B4 does it for you, or it can help you with it. You can like I said, when you run Patman, it opens your editor with all the patches before sending them. Before you have to manually, you can say before send -o to attempter, and it will show you what all the patches look like, but you need to do that yourself and look through them. And you also need to manually call check patch on all those patches. And so, yeah, or is there some automated way to do this that I don't know of?
I think it's being added now, so there's a before prep -- check.
Oh, cool, okay. I didn't see it when I looked earlier, but maybe I missed it, or maybe, like you said,
Maybe it's on mailing list, so soon will be added.
Okay,
but
cool.
It's in progress.
I mean, that's great. I mean, every time things like this get added and get fixed, that's amazing. So, and there's also this cool before send reflect that you can actually send the patch that looks exactly like the patch will look, but only send it to you. So you can really see it in your email client and make sure you didn't look like too much of a fool. So I'll show you what, calling before send. I use the web endpoint to send it. And yep, it sent my thing. And after I sent it, it recorded the series message ID in the cover letter because it knows what message ID it got. And that's going to help it find it on lore later. It bumped the revision for me, updated the change log with some history, and did it all nice and quickly. And when I sent my patch via B4, you can actually see it's a little weird. Look at the from line here. So I used the web interface for B4, and it can't send patches from me without my SMTP server. So it actually sends it Douglas Anderson via B4 relay. And that's fine. People, this is a kernel.org tool. So if a kernel maintainer yells at you for your patch saying that, you're like, dude, no. It's like, this is officially supported, officially OK. And then it says from dev null plus dianders.chromium.org at kernel.org. So it can send that fine. If you have a kernel.org address and you use B4, then it doesn't do this. And B4 can also use an SMTP server, and then it won't do this. So this is only if you want to use the web submission interface. But you can see all the raw data. There's B4 tracking and my key tags, and the message ID. You can see here's my branch ID, here's the date I sent it, here's the version. So it does create this nice message ID as well. And I think this is the base branch that I based on, the commit of the base branch I based on. Oh yeah, it is, because it also shows it down here. Once I send, B4 updates the metadata for you. In your cover letter, it says, hey, you need to edit and add some new change logs. And then like I said, it updates your revision for you and does stuff like that. Adds some history of what all the old change IDs and things were. Now, one thing that I'll notice here, I'll mention here, I guess maybe I'm cutting to the chase a little bit, but B4 really, you can see the version history here is really on a patch series basis, not on a patch by patch basis. So on B4, it helps you and encourages you to just send version history in the cover letter, and then it's up to you to figure out if you want to add version history per patch. And if you do that, you have to do that all yourself in your own formatting, right? And so it's a very different approach to how Patman works. Patman is really focused on that version history on per patch, and the cover letter is just the aggregate of them. And B4 is really helping you keep track and give you that nice final cover letter version history, but doesn't give you any help at all for the per patch version history. So more and more, as more people are using B4, I notice that they don't tend to have version history in each patch, which is a little annoying to me, but whatever. Let's see, did I say anything? No, I already talked about this. Automatically adds a link, which is amazing. It puts the base commit in there, which Patman, I think that's a Git feature, but Patman doesn't do it. And it's got a change ID to help bots out.
Yeah, you forgot about the tag. It creates a tag automatically.
A tag, oh.
Which is cool because it creates a tag with the patch. it creates a tag.
A local Git tag?
Yeah, you on the previous slide. When you send the.
Oh, I may not have copied that part. Oh, up here.
Yeah. So it sends a tag. It creates a tag on top, tagging, which
has
the patches
yeah.
without the empty commit.
Okay.
And the cover letter is in the tag description.
Ah, okay.
So in fact, you can rebase other code on this tag, and it won't conflict because you cannot add a before empty commit on another branch with an empty commit.
Okay.
So if you want to accumulate multiple patches, patch series, you can use the tags, merge the tags, and add another patches on top.
Ah, okay.
Which is really well designed, I mean.
Okay, cool. I didn't know that. I mean, like I have, like I said, I've barely used before because I've been using Patman for so long. So thanks.
If you have a lot of patch series on top of like upstreaming SOC support, for example, you can have all these tags, merge them on top, and add your own work in progress on top, and it won't collide. Everything is fine, and you don't won't have to cherry pick every patch manually. So it's a good feature.
Cool, thanks. So comparing and contrasting. I mean, I've already kind of been doing this throughout the whole thing. They're both great tools. I think, honestly, both of the tools could adopt the stuff from the others, and that would be amazing. And hopefully people, see this and they're like, oh, that's a great Patman tool or feature, or that's a great B4 feature, and add things to them. That'd be awesome. But the major difference and fundamental design difference is just the Patman sticking the tags in each individual commit, and B4 having that one big metadata thing. And I guess maybe one or the other could try to adopt something like that if people really wanted to, but it seems like that's really the fundamental difference between the two. And so why you might want to use B4 if you like that empty commit, there's a lot of nice new features that B4 has, and it has the very tight integration with lore, which is great. It's also 100% no one could ever complain to you if you sent your patches with B4 and B4 did something weird, because you're contributing to the kernel, and it's a kernel.org officially supported tool. So the no SMTP can be nice, and all that stuff. Patman, like I said, I really like the version history, and sort of things getting tagged in individual commits kind of speaks to me. Having all those tags there is nice for me. And for me, the change ID is kind of the deal breaker for B4. I really, that's just my workflow, is to work in the same kernel tree, and having that Garrett commit hook is just always going to be adding change ID back, and I'm always going to forget it. So having that stripping is nice. It wouldn't be hard for B4 to do that, but it doesn't right now. And I like some of the automated stuff that it does as well, like automatically calling check patch and stuff. And that's it. So thanks for coming, and hopefully people found something interesting.
One more thing for B4 is that it uses the patch attestation. So when you send the patches, its cryptography signs them, and then when you apply, the maintainer applies the patches through B4, then this attestation can be checked. So I guess Patman doesn't do this.
I mean, you just get DKIM checking, right? So
yeah.
Presumably DKIM checking is still pretty decent.
Yes.
Because if you're sending your SMTP server, and that's theoretically authenticating who you are.
Except when you use Google for sending, because Google rotates the keys, and after 1 month,
oh, is that why DKIM always yells at me for Gmail stuff?
Yes.
Or occasionally yells at me and then stops yelling at me and then starts yelling at me?
Exactly. Yeah.
Oh,
I mean, this is actually a problem, I think, the Python tool, because it checks the, Google rotates the keys, and the keys is not valid anymore, and the tool respects this, and the tool should just ignore this invalid time, like not valid after.
Got it.
But several maintainers are confused about this, so even top maintainers refuse sometimes to take patches, also from us, because we use sometimes Google server.
Right. That would that still be a problem if you used B4 and used SMTP, or it still signs it?
The problem is for the Gmail server. So if you use the Gmail as SMTP.
Yeah, okay.
Yeah, so the patch attestation is separate here. Yeah.
So it's okay. If the DKIM fails, we add your GPG key and it.
Oh, that's true. Then so you can still work around maybe the Gmail SMTP problems if you sign it with your GPG key, which B4 can do.
Yeah.
Fair enough. Thanks. Sorry for being a little over time. Thank you, everyone.
Yeah, thank you.
Hello? Hi. Can you hear me? Yeah, I think so. Okay, I think I'm going to wait just 1 minute or so in case someone else is coming. Okay, so yeah, I think I can start. So welcome and congratulations for making it to the last session almost of the this long conference. So this is going to be a session about WPE, about building end-user applications for embedded devices and products. Some of you, I know you are already familiar with WPE, but still I'm gonna make an introduction a bit about everything because we don't know who is listening also on the other side. So first about me, I'm Mario. I'm a computer science engineer. I'm partner of Igalia as well. We've been presenting a few talks here in this conference, so you might be familiar already with this company. I've been involved in open source for a long while already. In GNOME, initially, I also worked for several years on WebKit, mostly around the accessibility stack and the WebKit GTK port. I've been also working on Chromium, and even if it's not mentioned here, I've been done also a fair chunk of work on Linux-based operating systems, in particular with one operating system called Endless, in case you're familiar with. Yeah, and I also, if you're familiar with the Dynamo Maemo, I also did my fair bit there, and Samsung's the Smart TV platform. These days, I'm sadly not doing anything of that anymore. I'm coordinating Igalia's WebKit team. So that's why this session is going to be less technical than other sessions like the one that my colleague Adrian gave yesterday. So about Igalia, in case you're not familiar, well, just a quick recap. We are an open source consultancy founded in Spain 23 years ago in the northwest of Spain, a region called Galicia. We have the headquarters in there, but we are actually fully remote right now. We are 140 people distributed in 20-something countries around the world. And we follow an unusual structure. We operate a flat structure where basically everyone is eventually meant to become a partner of the company. So it's quite unusual. And we made decisions on a consensus-based mechanism. We've been top contributors to the main web rendering engines for a while already, like started with WebKit, but then also Chromium and Gecko. And most recently, we took over the maintenance of Servo from Mozilla. If you came to our booth, you might be familiar with these concepts as well. But we also work on other open source projects as well, like JavaScript engines, compilers, even Node.js or the multimedia stack, like GitStreamer, or the Mesa and the Linux kernel, yeah. Because of this, we are also members of different working groups, like the W3C and the WG are the obvious ones, but then also TC39 for our working in JavaScript, and well, Chronos for graphics, several ones. So this talk, like I said, is not going to be deeply technical. So this is an outline of what's going to be about. So it's going to be a quick introduction to web rendering engines and in particular WebKit, and then going deeper into WP in particular, and then give a bunch of ideas and general ideas about what is important to take into account when integrating WP in a product if you want to build. So web rendering engines, I will probably be calling them web engines randomly, so that's why I make this clarification. So what is a web rendering engine? So I think the easiest description I can think of is just, it's a software component that basically allows you to use the power of the web platform to develop your products. So basically develop your projects with web-based technology like HTML, JavaScript, CSS. I think most of you are familiar with all that. So step by step, what it does, a web engine, like again, very high level, is it fetches the information from the network, from the multiple sources, like the document and all the different resources linked from the document. It then interprets all that web content and creates these internal representations to process them later on. Like in the case of WebKit and Chromium, is basically a forest of trees. Basically just initially like it has to determine first the tree of the different nodes, which is the DOM tree. And then with that, it has to figure out which of those nodes will be represented by visual nodes. That's a different tree. It's called the render tree. Then with that, it has also to take into account all the CSS rules, all different kind of things, and do a process that is called relayout, which is basically position everything in every different place. And then with that, it even creates a different tree, which is called a render layer tree, which is very useful in embedded devices because it's what allows you hardware acceleration by putting things in layers, sending them to the GPU so that it can be composited. And then eventually, that's the rasterization step, and things go out into the display. So yeah, and I'm not even talking about other trees like the accessibility tree. So it's really a forest of trees. With that, the web engine produces a result. And this result, the whole point is that the user can interact with. So most of the times, people are thinking of something visual, but it doesn't have to be. But this is the whole point. Like you produce something that you will interact with, either on a screen or via voice commands or whatever you can think of. So it's an extremely flexible platform, and like I was anticipating already, it's useful for textual and non-textual content, but even if you just want to leverage the web platform to, say, play some audio and you don't need a display, you can use it for that too. It's nothing that says that you have to use it to render visually something on a screen. And then, well, these days mostly it's also used besides web browsers for developing fully fledged applications in specific contexts, like in in-flight vehicle, in-flight entertainment, GPSs, and, well, many cases. So a distinction that I usually make, if you're familiar with that, forgive me, but I usually have to make this distinction. A web engine is not a web browser. It's a different thing. And in the case of other web engines, like the one that is using Chromium, it becomes a bit more confusing because people do embed Chromium. But in the case of WebKit, which is what we are going to be talking about, it's an important distinction. The web browser is what you build with a web engine, but the web engine is the component that does all that. It's not, the web engine is not the address bar or the back and forward buttons or that, and nothing like that. It's just the component. And these days, the most popular web engines are the one WebKit, which is the icon on the top left. Then Blink, I'm afraid there is no icon for Blink, so I put the icon for Chromium. So Blink is the web engine that is in Chromium. Gecko, which is the web engine used by Firefox, and Servo, which is this other web engine that is written in Rust, and that, like I said before, we took over from the Mozilla Foundation. So what is WebKit? It's an open source web rendering engine. These days, maybe it's not that relevant to say open source because most of them, or at least most of the relevant ones are, but back in the day, it was not the case. We have Presto for Opera and Trident for Internet Explorer, so it's still a relevant thing to mention. It started as a fork of KHTML and KJS in the 2001, which were the web rendering engine and JavaScript engines used in KDE for the Conqueror browser, if you're familiar with it. Back in the day, WebKit was used mainly for Apple, but then Google also joined because it was used as the basis of Chromium, the Chromium browser as well. And then in 2013, it got forked by Chromium and renamed into Blink for the case of Chromium. Exactly before this point, WebKit actually had an architecture that even allowed two different JavaScript engines, V8 and JavaScript Core. But after this point, that was cleaned up, and now WebKit only uses JavaScript Core, just for reference. So the main goals haven't changed, has been in the website for a while. For WebKit are basically these ones, like performance is really important, and there is a very strict policy with zero tolerance for performance regressions in WebKit, so there's no way you will be landing a patch if the performance bots detect that there is a regression there. Portability has to be working in many different platforms, not just operating systems, different devices. Stability and compatibility is obviously a must. Standards compliance is meant to be a web engine that is compatible with the whole web platform, not just a subset. So it's very important also that it's interoperable with other web engines. Security is a big thing in WebKit, I will say in all web engines. WebKit's been always like one of the main themes. Hackability, this is a weird term, but it refers to the fact that it should be, I don't know if pleasant is the word, but it should be easy to get hacking into it. I mean, as easy as it can get to hack into a 26 million lines of code base, but it shouldn't be that much of a pain either. And then, and I will insist, embeddability, and this is one of the main distinctions between WebKit and, for instance, the Blink, which is using Chromium. And I will get into this in the next slide. And like I said, because of the portability, it's important that it's supported in different platforms. So that means desktop and mobile. Back in the day, it was used in many more use cases, of course, because Chromium was also used in many cases. But even to this day, it's not just used in Safari, as many people sometimes think. But then embedded, for instance, there's a lot of places where WebKit is being used. In set-top boxes is counted in the hundreds of millions of deployments these days. Video game consoles as well, like the PlayStation. Smart home appliances, like if you're familiar with the Thermomix, for instance, the cooking machine. Yes, when you cook, you're using WebKit. And then in vehicle, in-flight entertainment, GPS devices, digital signage as well. This is a really common use case where you have a big display just in shopping malls or in airports. That's one of the other things. So a few advantages of WebKit. One of them is, as I said before, it's a complete implementation of the web platform. This is relevant because there are other web engines that are not. These days, for instance, Servo is a very good use case. It's based on Rust and it's very secure, but right now it's not yet a complete implementation as WebKit. WebKit is basically at the same level than Blink for Chromium. The other thing is this one. It's embeddable as a top priority, and now I will insist even more. This is extremely important because in WebKit, the web engine, this component, is the actual product. So the whole point of WebKit is that you are going to be able to use the web platform in your application, in your product, regardless of what that product is. So for that to be able to happen, you have to have one thing that is mandatory. It's a clear and a stable API, public API. This cannot change. It cannot be broken across releases because that's the product. The idea is that you should be able to put this component in your product, build your project on top of that, and then be able to update to new versions of WebKit without breaking your product. This is a big difference. Back in the day when we started working on WebKit, Gecko was also the same thing. You could use Gecko to build your browser. But eventually, I think it was 2010, there was this decision that Gecko will not longer be like that. The Mozilla will be able to break the API anytime they wanted because Gecko was just meant to be used by Firefox. So as you can imagine, if you base your product that is not Firefox on Gecko, that was a pain to maintain. So WebKit, on that point of view, was really useful because it guarantees the API will be stable. So this also means that it's self-contained. So you won't have anything outside of WebKit that you will need to be running WebKit. So it's really good on that point of view. It has a flexible and modular architecture, which also is what allows us in Igalia to create this product, WPE. The fact that WebKit is self-contained, but at the same time it has a very clear architecture that separates clearly the platform-independent code and all those abstractions from the platform-specific layers. And you can adapt to different platforms. So that makes it, I won't say easy, but it makes it feasible to be able to develop a product like WPE. That I will get more into detail. Well, like I say, privacy and security are big concerns in WebKit. So this has been a motto since the beginning. So it's an advantage, I guess, against other web engines that are not as secure. But don't get me wrong, this is not a comparison against Chromium, in case you wonder. It's just advantages that you get by choosing WebKit. Performance and stability, like I said before, I won't insist more on that. And this last one, I also think is a very important one. All the Linux-based flavors are independent, meaning that they are not controlled by any big corporation. So this means that if you have, and it is combined with the fact that this is an open source project, means that if you want to develop a product based on a web engine and on a Linux-based device, and you have it's much easier for you to push things upstream that are on your interests. You don't have to fight against the interests of one or two single big corporations that might not might not find it interesting to get your changes applied. So in this case, it's an independent web engine. So the architecture 101, really simple. Like you have your application at the top, which is what you are building, and then you just go against this clean and stable public API, which is this thin layer that we call, inside of the whole WebKit thing, there is this layer at top that is what we call the WebKit API. It's all you need. Underneath that, there is all the chunk of all the other 20-something million lines of code, which is web core is the part that is platform independent and is the part that implements all these algorithms for fetching, for parsing the DOM tree, parsing the CSS rules, creating these trees that I mentioned before, all that without assuming any specific platform. And then when it comes to putting that into actual pixels or fetching the bits from the network using a specific library, then is when you have to implement these platform-specific hooks in what we call the platform layer. But this is quite separated from the web core part. And then on the side, there is the JavaScript engine, which is called JavaScript core. Back in the day, you could choose this one or V8, but it's been 11 years since you cannot do that anymore. And with that in mind, the description, the obvious description before getting into WP is a WebKit port, which is a WebKit port. It is an adaptation of the WebKit engine to a specific platform. So basically, what in the picture before, if you take that box at the bottom and you make it specific for the library that you need on your target platform, that's what basically makes a port, along with all the rest of WebKit. These days, there are a bunch of official WebKit ports. So the ones for Mac and iOS, those are the ones that Apple maintain for the obvious, the usual suspects: Safari, Apple Mail, iTunes, and same thing for the iOS. There is the WinCairo port, which is for Windows, and this is a port that is mostly used these days as a component for the PlayStation SDK by Sony developers, and it's maintained by them actually. And then there is the PlayStation port, which is on the PlayStation 4, and this S4 is a typo. It's PlayStation 4 and PlayStation 5. And then there are the last two, which are WebKit GTK and WP, which are the ones used in Linux environments. WebKit GTK more in the desktop, and WP on embedded devices. So these two ones in particular are not just, they don't have only in common that they are for Linux-based system, but actually, they have a lot of shared libraries and shared paths. And actually, the WP port kind of started as taking WebKit GTK and removing the GTK out of it, and simplifying it so that it could be used in embedded environments with more constrained requirements. So the common parts, like all these libraries, like glib, which is a library for all the basic functionality that you would expect from a C library, or from a C-based environment. libsub for networking, those are shared. GStreamer for multimedia, they share that as well. It's not mentioned here, but in the previous version of WebKit GTK, ATK for accessibility as well. ATK is not used anymore for newer versions of WebKit and GTK, but when it was used, it was common parts. But there are key differences, and the main difference is on the input and the output. So on WebKit GTK, it assumes the GTK toolkit, and actually, if you are familiar with GTK, what it does, what it gives you is a widget. It's a GTK widget that is the web view that you can embed in your application, and you are set. Well, you're set. You get the component, then you can interact with it through different APIs. But basically, you get a widget that you can add to your window. And then the input handling. In the desktop, you expect to use it like with a mouse and a keyboard. In embedded, it depends. So in the case of WP, that's abstracted to backends. I will get into that later. So WebKit GTK these days is considered the go-to solution for embedding web content on GTK applications on a desktop, and also integrates really well with GNOME by supporting GTK3 and GTK4. But in WP, instead, is much lower level and aimed at embedded devices, and requires that you specify what graphic and input backend you want to use. So taking just to finish this section, taking the diagram from before, if this is the generic WebKit thing with all these layers, when you change those boxes, that's what makes a GTK port, right? You provide the platform-specific hooks, so libsub, Cairo, GStreamer for in this case for network, 2D rendering, and multimedia. Also, the API layer is specific to WebKit GTK because it provides a GTK widget. In WP, is different. And then you have a GTK application. So that's what makes a port. So with that out of the way, so what is WP? It's a port optimized for embedded devices based on Linux. So it's some interesting things about this is provides you with a fully operational JavaScript engine. It's fully operational and supports 64-bit architectures, and also is maintained for 32-bit as well. Only that in 32-bit, you don't have all the optimizations that you have available in 64, but on just basic ones. But it's still guaranteed to work, and we are maintaining that. And there is also some initial support for RISC-V, but I don't think we can get onto that now. Then the second point is that, besides the focus on security and performance that is general from WebKit, WP is very focused on being flexible because you don't know what kind of device you are going to work on. You don't know what kind of hardware you're going to have to work with, and that basically determines also your input and your output. So In order to work like that, it has to be very flexible, and that's why first of all, we did try really hard to reduce the amount of dependencies to the bare minimum. That's one thing, so that you don't need to put too much stuff on your device. And the second thing is that we designed it with a backends-based architecture, so that you can plug different components depending on the input and output you want to use. We provide already some default backends, so that you don't have to reinvent the wheel all the time, but that nothing really prevents you from adapting in that backend to your needs or even creating a custom backend. It's something that we've done a few times already in the past. The other point is that we have a big focus on low memory and low storage footprint for obvious reasons, like because when you have devices like the Raspberry Pi 3 or an IMX6 board, things like that, you really cannot count on having gigs of memory and really a lot of processing power. So that's another big focus on WP. And finally, we also support hardware acceleration, graphics, and multimedia. We do big efforts on that as well, because we understand that as much as we can relieve the CPU for doing work, that's always going to be for the better. Unfortunately, not every single board we can do that, because not every board supports the APIs that we need. But whenever those APIs are available, we try hard to use them. Like, I guess a good example is, most recently in the last couple of years, we implemented support for DMA buff that is being crucial in terms of avoiding extra copies. Not just for graphics, for communicating with the GPU, but even on the multimedia pipeline, we use DMA buff as well for passing things between the different steps of the multimedia pipeline and avoiding copies as much as possible. And what is not WP, and I like to insist on this as well, it's not a general web browser. It's just that component, and it's not meant to be. So it just gives you the building blocks, but as you cannot expect to build WP and then have, you don't even have a launcher, or you need something else to put the web content on the screen and be able to interact with it. This just provides you with the building blocks. It doesn't implement all the APIs. What this means is that in embedded environments, it might not make sense to have all the APIs that you have available in a desktop browser implemented. So basically, we are implementing them in case, whenever we have a need or we detect a need, they are implemented. But there are some APIs. I think a good example is the pointer lock API that it hasn't been implemented for a while. I don't know, is it implemented already, Adrian? But it's been recent, right? Last 3 months, there you go. So the pointer lock API, if you are familiar with it, if you're not familiar with it, is what is used in games, for instance, in games like shooters, where you are playing, you don't want the cursor to be messing around, you want to use the mouse to change your view. So you need to lock the pointer. And that was not a need until recently, because on embedded, on a set-top box might not be the use case that you wanted to do, but it's being detected as a need recently, and it's being implemented. But there might be other APIs that are not implemented, but there's still a lot of coverage. It doesn't rely on any particular toolkit. This is by design. Like I said, you don't get a widget, you don't get nothing like that. You get just a component that allows you to render some content into a display where you want to put it, and also allows you to interact with it. And because of this unconventional approach, it can also be useful for less conventional use cases, like server-side rendering, where maybe you get a video feed and you want to overlay something on top, and then the result ship it to from that server to some other device, and you do that on the server. That you can do that. Headless mode, you might have an audio system, a hi-fi system, where you just want to use WP to consume a multimedia endpoint from a streaming service to get the sound and put it through the speakers, and you don't need a display. So it's very convenient for that. So the architecture of WP is basically, obviously, is kind of what I showed before, just with a twist. Is you get the application, you get the WebKit port, but you also get these backends in the middle, which are the platform specific implementation for how you want to use the output and the input layers. So with this, going through the components of WP, so there are 3 main components, four, if you want to consider also the final step that you need. So the first one is what we call WP WebKit. This is the actual WebKit port. Technically speaking, this is the WP WebKit port. That is actually, the code is in the upstream WebKit repository. It relies on the backends for page display and input. I can say there. But how you do get the display rendered on the screen and how you deal with the input, you need to abstract something like that. So you have this other component, LeadWP. What it provides is just the glue between the port and the backend. So it gives you rendering-related callbacks that are called from the WP port and are implemented by the actual graphical backends. And it also gives you a way for the input backend to relay events from the application to the WebKit port. And the other component that we ship is the WP backend FDO, which is a backend using free desktop technologies, like Wayland, for instance. Finally, you need a launcher. So we also provide this launcher that is called Cog, which is basically it provides you with a small window. Doesn't have user interface, just render the content, the web content, but you also can interact with it if you want through libus with a cog.ctl command line tool that we also provide. But it doesn't provide you with an address bar or a back and forward, basically just a place where you get everything rendered on a Wayland environment. So some examples of use cases that we are aware about, set-top boxes, smart home appliances. I think most of them I already mentioned them, so I think I will skip. The last one, QA and testing, is also used in headless mode, for instance, by the Playwright testing automation system, basically to make sure that to be able to run your test for different engines, Chromium, Firefox, and WebKit. And in the case of WebKit, some of the tests are used running WP because it allows this headless mode. So yeah, well, I have here a demo. If you've been in the booth, you've already seen this one. So this one shows a bunch of WebGL examples that are running on a Raspberry Pi 3 board. So these are fairly old demos, but they're still good to showcase how it enables lower power devices, right, to run complex WebGL applications. So the point is that the CPU remains low all the time, and while having a decent rate of FPS, a decent rate for a Raspberry Pi 3. And obviously, if you get a Raspberry Pi 4 or 5, it goes faster, but the whole point is that it allows you hardware acceleration. And the second demo, this one is showing WP playing HD video and applying different transformations, like splitting the image, doing translations, scaling, all those kind of things in real time, sustaining, again, a decent rate of FPS. This is a fairly old, but I keep showing it because the device is so constrained that it still amazes me that it works. And this is a really old version of WP. These days, it's even more performant. So if you want to integrate all these things in your project, what are the things that need to be taken into account? I had a much bigger description, but Adrian yesterday did an amazing job in his talk that I recommend you to watch in more detail on what exactly to do. So if you are looking into a more detailed, more deep down description, I recommend you to watch that talk. But basically, it all boils down to a few steps, higher level. Like first one, you carefully choose your hardware. Sometimes you cannot choose it freely, but as much as you can, this is probably one of the most important steps. So you need to determine the specifics, the characteristics of the hardware you are going to be relying on. Be aware that different hardware have different constraints. So it might impose different restrictions. Like, I don't know, we know for a fact that there are certain boards that don't allow, for instance, tiled direct scan out. And you have to put everything on a linear direct scan out that basically prevents you from running certain optimizations. So if you have a choice and you can choose a hardware that is better suited for your product, the better. If not, WP can adapt. The second one is to determine the input devices you want to use. This is basically how your users are going to interact with your product. So it's another important thing as well. And it's also what is going to determine what kind of backends you are going to need. Exactly the same thing for the output devices. So determine what kind of displays. Most of the time, people are thinking always on HD or Full HD or 4K screens, but with standard resolutions. But you can also be using LED displays with random aspect ratios which is very common, for instance, for digital signage. And those things also impose certain restrictions. Or like Adrian mentioned yesterday, specific rotations that you might need to run because the display is not arranged as you would expect. And once you have all that information, the other thing is figure out whether you need custom backends or you can use the ones that are already available. The second part is to assemble the required components. So the first obvious one is you need the WP libraries. The current API has 3 components, as we saw before, the WP WebKit, which is the port, the libwp component, which is this glue between that and the backends, and then the backends. Right now, we are working on a new API. This is not an announcement, so don't quote me on that, but we are working on this, and the idea is to have it ready as soon as possible. We hope we'll be ready soon. I don't want to say anything, but it's moving very fast. And the whole idea with this new API is to make it even simpler, because we detected that all this flexibility with WP, WebKit, LibWP, and all the backends is great, but it also imposes certain complexity to work with WP, that we are aware of it. So the new API aims to simplify that much more. So ideally, you only have to worry about the WP WebKit component, and this WP platform that you are going to get also, it's going to be treated as one thing, and you don't have to worry, in many cases, not even about the backends. So that WP platform will be able even to automatically select them. Then obviously you need to provide a rootfs image that has all the dependencies for 2D rendering, for multimedia, for networking, for all the usual stuff. It's very important to have support for OpenGL and EGL as well. And then, obviously, any other library that you might need for your purposes. At the same time, you also need to have a launcher application. You can use Cog, that is, by the way, is using the old API, or you can just roll out your own application. And rolling out your own application at a very basic level with the new API is as simple as this. It's basically just, this is a simple example. I think you also showed it yesterday. So just to walk through it, it basically creates a main loop, creates a web view. We pass null, which means in the new API, it means that you are letting WP select the right backend automatically, and just loads this URL, and that's it, and it will run the main loop. As simple as it gets. And then once you have all that, you basically have to, well, you have to do your job and develop your project. The nice thing is that because it's a web environment, you can also prototype and write it most often even on your desktop machine, and then you can, obviously you have to test it on the target board, target platform, but this is the other nice thing about working with web-based technologies. As much as it pains me to say this, I think we also need to be honest with ourselves. The devices that we are using most of the times are very constrained, so I think if in some cases it might be important or it might be convenient to acknowledge that oh, my device is not particularly good with this particular type of operations, like a blur operation. So maybe, I mean, yeah, WebKit can be optimized, that's true, and we do everything we can. But in some cases, there might be also alternative ways of implementing your application. So if that's a possibility, we also recommend to be aware of those things. Because sometimes we find applications that are performing really bad, and it's not because there is something fundamentally wrong with WebKit, but it's because the particular hardware is particularly bad on this very expensive blur operation. Then we tell the customer, look, try this other operation. Visually, it's going to be very similar, and then the performance improves like a lot. So yeah, it's basically a trade-off when you are working with embedded devices. Integrated with the rest of the platform, this is, again, what you were mentioning yesterday as well, the possibilities that you get your web application, but you want it to interact with the rest of the platform or your devices, and you can use all kinds of things like a custom URI schemes. It's an option, or user script messages, or just JavaScript, plain JavaScript APIs. That, by the way, you can also implement your own in WebKit if you need them. And finally, testing and QA, another very important thing. And in particular, these hardware platforms impose different restrictions, and testing automation is also very important for this. So we are also working now on improving the WebDriver part of WebKit that should allow to get much better or pleasant way of implementing complex tests that are not with WebKit done before. And finally, just bundle it up and ship it. You have several ways of getting WPE, from distribution packages to the source code, rough source code from the different repositories. Or if you are based on Yocto or Buildroot, you can already use create your images based on the layers that we are providing. So for the case of Yocto, we actively maintain these ones. They are available on that link, and it's the recommended way. But Buildroot, there is also support available. It's just not, we don't maintain that much as Yocto, so it's mostly on a best effort basis. But they are there, and you are always welcome to submit patches or report issues. And if you have some time after all this mess, if you can collaborate upstream, that's always more than welcome, because many times we don't know that a problem is a problem until someone tells us. So yeah. There is some documentation, API documentation. Documentation is a sore spot of WP. We are trying progressively to fix it. Recently, we uploaded some documentation to the website that was not there as of 2 weeks ago. And we plan to keep improving that one. But then there are also other useful links there, like the security advisories or the mailing list. And that's pretty much it from my side. Just as a conclusion, this is what I think I would like to communicate with this talk, that the web rendering engines are not just for building web browsers, as many of you already know. That with WP, you can get all the strengths of the web platform, but also adapted to embedded devices, thanks to this extra flexibility. That if you want to integrate WP in your product and you want to get an optimum result, it's not just a matter of improving WP, which is also, or WebKit, which is also very important, but it's also a matter of being aware of choosing the right hardware and being aware of particular issues that you might have to avoid in your particular hardware. If you combine that with ever improving web engine, that should yield a really good product. And then, yeah, just develop your application, knowing that adaptations are always possible. And yeah, and a last reminder that it's fully open source, so contributions are more than welcome. And that's it from my side. Sorry, I think it took a bit longer than expected. Any questions or comments? Yeah?
Cool. I saw you had like the video piece there. Do you know if there's anything with the WebKit to support making applications support like to H.265 codec and output in like MPEG-H, like more later standards, anything like that? Or where we could find resources on that?
So yeah, actually it's a good point. I haven't insisted that much in this talk. I mentioned very briefly about the multimedia support, but multimedia is actually a very big part of the WP port. In one of the main use cases is the set-top boxes. Oh my God, so many slides. What is it, this thing? Yeah. Well, whatever. One of the main use cases is set-top boxes, where multimedia is very important. And because of the use cases that you have there, you have to support things like encrypted media extensions or media source extensions, all kind of DRM-based playback to be able to stream your favorite services. So yeah, there is a lot of support for that in WebKit. And you can also use different codecs. You can use H.264, H.265, V8, V9. Obviously, that depends on the platform that you have underneath and having the right driver for the particular hardware that you have. But yeah.
If I may add, because we rely on GStreamer for the multimedia operations, if your platform happens to have an accelerated codec that plugs into GStreamer and it works outside of WebKit, there are very high chances that WebKit will also pick it. WebKit will claim to support any video format and any audio format that it can find a GStreamer plugin for. So from that point of view, it's not a fixed set of codecs that WebKit would support. We basically ask GStreamer, tell me what you can decode. And that's everything that is supported. So if there's new video formats or some video format that is not like a standard web format that is supposed to be baseline supported, you can always have extra formats based on what GStreamer plugins you install.
Okay. Any other question or comment? Okay, so, oh, yeah, sorry.
I guess this is the embedded conference, so I probably shouldn't ask this, but like as far as more like userland Linux desktop software, are there kind of common apps or like popular apps that use this that you know of?
In the GNOME environment, I mean, pretty much any application that needs to render web content uses it. Like if you're familiar with GNOME Evolution, for instance, is the mail client, it uses it. DevHelp is the developer documentation client, also uses it. Shotwell, I think it does. Pretty much anything that needs to render web content uses it. I think the Matrix client, does it use it? I don't know. No, I don't know. But pretty much any application that needs to render web content uses it in GNOME. Back in the day, I would say there were even more. But it's true that some of them have moved into other web engines. But that's not I don't think it's something that strange from the point of view that in desktop the resources sometimes are not an issue, and you want to have something more similar to a fully fledged browser, in which case other options are also reasonable. But in the particular case of embedded, where you need to be very, very careful with your memory and storage uses, it's a different story. Yeah.
Sony was showing embedded web ASM stuff. Forgive me, I don't know if WebKit supports web ASM or if that's only Blink or WebAssembly.
Yeah, it does. It does support WebAssembly, yeah.
Yeah, but to elaborate a little bit on that, WebAssembly support depends on some architecture-specific code. So, for example, the newest supported architectures like RISC-V that Mario was commenting that is recently it got support in JavaScript core. Right now, it cannot run WebAssembly, but the ARM and x86, they both can run WebAssembly without any kind of issue.
What about tools for profiling? Like use existing tools, or you guys have any specific tools to help the web developers, let's say, pick the correct frameworks for the web backend that are gonna work well on embedded?
Yeah, so for that, similar to other options, in WebKit you have the inspector, right? You have a similar inspector to the one that you can see in Chromium, where you can inspect all the code. You can also inspect network requests. You can inspect the JavaScript events, all those kind of things, even how frames are being rendered in different points. If you need to go deep down into even how the frame synchronization process, you have all that information through the web inspector. It's true that that's very useful and very convenient to use when you are on your desktop, but when you're in embedded, it's different. So that's why we also support a remote way of using the inspector. So before, originally, in order to be able to use the inspector on a WebKit-based browser on embedded, you needed to use another WebKit-based browser to connect to it. But we have, I think you mentioned it yesterday as well, Adrian. We have implemented a different way of doing it over HTTP that basically allows you to use the web inspector from any browser. You don't have to use Epiphany in the case of Linux or Safari or whatever. But yeah, you have if you're familiar with the Chrome developer tools, it's pretty much similar in the case of WebKit.
I would like to add that there's a couple of features from the WebKit Remote Inspector that there are similar things also in Chromium for the You can do timeline recordings. This is the thing you were commenting, that you can get an idea of how the rendering process is happening, which parts of the code are taking more or less time, if it's going to spend time in JavaScript or in painting a frame, etc. It's a little bit hidden because it's in a tab that is not very prominent in the remote web inspector, but it's there. And then another one that I have not seen in other browsers is the layers inspector, because WebKit does this thing that it tries to offload composition of some of the content to the GPU as much as it can. So if you do 3D transforms, for example, they're going to run in the GPU always. And you can, from this inspector, you can see which parts of your content WebKit has decided to split in separate layers to composite on the GPU. And if you are having trouble with animations that run slowly or blending operations and so on, you can use some CSS tricks to get them into different layers, like abusing a bit the heuristics that WebKit uses to move objects into different layers. And then you can get the benefit of having them composited in the GPU. And you can also see how much memory is being used in graphics layers and so on, and which, like, it tells you exactly which CSS selectors are picked for a layer and which reason there is for promoting that content to a layer. And this is a feature that is not very well advertised, I think, and not very well known, and it can be quite handy.
Yeah. Just a quick side note, because we have to finish. It's been very useful. For instance, we've been working on a new SVG engine that the current SVG engine on WebKit unfortunately doesn't allow hardware acceleration because everything goes into a layer. So if you animate SVG, different parts of an SVG, everything has to recreate the entire thing again over and over again. And the new engine, what it does is put things in different layers, and these layers are sent to the GPU for compositing, so it's much faster, much smoother. And why I'm saying this, because this thing that Adrian is mentioning, this particular tool, is being very usual, very useful, for working on that particular feature, because it allows us to really see how things were being putting in different layers as they should. Any final question? I think we have to finish.
Real quick question. As far as switching from that custom inspector protocol to HTTP for the remote inspector, what version did that get introduced on?
It's been a while already, right? 2.40, I think. Year and a half ago. 2.40, yeah.
Okay, thank you very much.
You're welcome. Okay. So we
just
have
one last thing. If somebody's trying to debug media issues, there's also support that comes from GStreamer as well to dump the GStreamer pipelines being used. And we have some documentation now in docs.webkit.org about how to get a dump of those, and you can generate a graph of the pipelines so you can see which codecs are being used and so on to make sure it's the accelerated version ones. And this will be more like a lower level answer, but I know JavaScript Core has also some features that you can dump the generated code by the just-in-time compiler, but I have not used it much. I know it exists.
Yeah.
So there's also even more lower level debugging features that might be handy.
Yeah, if you have more questions, I mean, we're going to still be for an hour in the booth area in E28. So or feel free to send us a mail. We have to leave now because the next speaker, we are a bit late. Sorry about that. Thank you, everyone. Sorry.
No problem.
Gracias. No. Sí. Check, check, check.
Check, check.
Okay, hello. Not much left, last talk of the day before the closing game. Hi, for those of you who saw my previous talk 3 hours ago, nothing has changed. My name is still Bartosz, and I'm still with Linaro in the Qualcomm landing team. I've been around for some time. I've been doing open source for 15 years professionally. I maintain the GPIO subsystem in the kernel. I maintain a couple of drivers. I maintain a user space project that's called libgpiod. And I have worked for some time in the open source, which made me aware of the problem that is technical debt. And this is what is going to be subject of my talk. And as I said, I'm with Linaro. Thank you for having me here, and thank you for letting me work on interesting subject. Please check us out. We make software run on ARM. So my talk is going to be about technical debt. Probably everyone has encountered it in one way or another. And what is technical debt? The best way to describe it is by making a parallel to financial debt. So financial debt, you need money now, you borrow it, and then later on you pay it with interest, meaning you pay more of it than you borrowed. Technical debt is not different. So what you really borrow is time. You need to ship something, so you choose a solution that is suboptimal, but that allows you to implement something faster and ship it sooner. But there's going to be a penalty, which means that because of the suboptimal solution you chose, you will have to probably down the line spend more time to backtrack or improve this solution eventually to make it work, to make it more generalized and make it work in more cases. Just like financial debt, when it's time to pay back, you can actually decide to take on more debt and eventually pay even more interest. This works similarly with technical debt. You can just stack workarounds and continue using suboptimal solutions, but that will mean that eventually you will have more and more trouble maintaining that code. And just like with financial debt, not every debt is wrong, not every debt is bad. You can borrow money now, you can have an idea for an investment, you can invest that money, and the profit that you will make on that investment will actually be higher than the interest you will pay on the loan. That also makes sense in software. There's, however, good technical debt and bad technical debt. And in some places, for instance, in implementation details, using a worse solution may actually not be that bad because it's easy to improve something that is behind a programming interface. But whenever technical debt is used when creating exposed data structures and programming interfaces, this is where the problem starts. So imagine that you want to start working on and yes, all images have been generated with generative AI. Imagine you want to start working on some project. And I'm not talking about starting a new project from scratch, not necessarily, but you just start working on a piece of software. So there's going to be typically 3 categories of a starting point in every project. So everyone who likes their job, and like who here doesn't like their job, who doesn't like coding? So we're all probably passionate about software development. So the best thing that can happen when you start a new project is when you have an empty plot of land and can start working on your masterpiece exactly like you imagine it. You're doing everything from scratch. But this is rare. Like how many people have started a project from scratch and it took off and it's used by people? Well, so as you can see, this is quite rare. So the next best thing is a project that is well established, that may be complex, but actually everything fits together. It's well maintained. All the APIs do what they do what they should, and work correctly. And of course, it's complicated. Sometimes you need some deeper knowledge in order to get into it, but all the pieces fit. And then the third case is when you take over a project and it looks more like this. So it's different things stitched together. You're wondering what this or this part does, and then you try to modify something, but every time you just move one piece, everything crumbles. We would call it brittle code, right? So even if you start from scratch on an empty plot of land, it's not uncommon to see your project evolve into something complex and hard to maintain, even if on the way you have some refactoring attempts. So why does it happen? When you start a project, you will not necessarily be aware of all the use cases it will face, especially if you start a project that will solve a problem you encountered, and then all of a sudden people start using it, and the users use it in so-called wrong ways, so in ways you never imagined that this project would be useful. Then they will come to you and ask, okay, so can we implement this or that feature, or even provide patches, hopefully, for this or that feature? And you cannot really predict all these new things that users will come up with. So next thing is that almost in every kind of software, whether you're talking about a monolithic kernel that officially doesn't have any API stability or a C library that you expose to user space, you will have to maintain some interfaces because, let's face it, we don't change interfaces all the time when we have users of our code, when we have active users in the field of our code. So you need to maintain some stability for old use cases. You need to introduce new features. Possibly you have provided some interface that is now hard to extend. And even the Linux kernel that, as I said, officially does not have any stability. If you have 1,000 users of a function, then changing that function to something new is not going to be that easy. And then you have the user space ABI in the kernel, which officially never changes, which will lead us to introducing new ABIs instead of removing or modifying old ones. And then there's another thing that is simply not being grumpy enough as a maintainer. And just as like we heard with the recent XZ backdoor, where the maintainer has basically been bullied into accepting this or that change and then eventually relinquishing his maintenance. There is a reason why maintainers are and often should be grumpy. And if you look at Krzysztof, he's the nicest person ever in person, but when you encounter him on the mailing list, you may not get that impression. So whenever business priorities take over and you accept code without demanding it to represent a certain level, that stacks up over time, and you end up accruing technical debt. So some kernel-specific issues. The ABI and API stability. So API, just like I said, when your subsystem in the kernel is being used all over the kernel, it becomes really tricky to change anything. This is why many subsystems will have 2 iterations of an interface, a programming interface existing at the same time, because it's just simply so difficult to remove or modify, port the old users to the new API. And the user space ABI, as long as the user space tells you, oh no, I was using this, why did it change? You have to go back. So you literally have to support your user space facing interface forever if needed or if requested. And then we have, the kernel is officially monolithic, but it is not really logically monolithic. What happens is you have to look at it as different libraries with different users of those libraries. And now we have kernel subsystems where people come up and say, okay, so I will implement a new subsystem. But instead of doing it in a way that will address this specific problem, people usually what they do is just copy and paste existing solutions and repeating the same mistakes. So you basically duplicate the existing technical debt. But also, people often will not reuse solutions that exist that are good and instead introduce something new, even though they should have used an existing piece of code. And a personal pet peeve of mine in the kernel is lack of a good deprecation mechanism. So we don't use GCC or compiler attributes for emitting warnings whenever someone tries to compile a deprecated symbol. We have check patch, but it is first, modifying anything in check patch is quite hard, and I haven't seen many people use add symbols to check patch that should warn on using deprecated functions. And documentation is for most part ignored. So in the subsystem I maintain, I've had deprecation warnings for symbols for a long time, and people still even every now and then try to use symbols that should not be used. I maintain the GPIO subsystem, and it's a very good example of how technical debt adds up over years, how it stacks, and this is a subsystem that has existed for 2 decades, and I don't think it's avoidable to introduce issues with technical debt over such a long period of time, and especially, as I'm going to show, the GPIO subsystem has everything going against it. So back in the day, way before device tree, way before even the driver model existed, we had board files for various platforms. So back then, GPIO wasn't a subsystem. It was basically a way to toggle pins, and people introduced a certain semi-standardized number of functions that would request a pin, set its value, read its value. And then these would just be the function prototypes, and you would, like different architectures would implement those symbols as C prototypes, and then they would implement them in Summer. So later, the GPIO subsystem evolved into a provider-consumer model, but based on a global number space, simply because those numbers were already used in these initial semi-standardized symbols. And eventually, the subsystem evolved into a proper modern kernel provider-consumer model with framework with opaque descriptors for GPIO lines. But it doesn't change the fact that the old code existed and the new came on top of it. So internally, we're still using the global number space. Internally, externally, the old interface is still there and is still supported. And last time I saw, something like 35% of all GPIO consumers still use the old interface because it's simply so hard to convert them all. Also, over the years, the GPIO subsystem had periods, well, had many maintainers before, and also had periods where there were no maintainers at all. And important decisions were made during the time where there were no maintainers, like for instance, merging the SysFS interface was done when there was no maintainer active for the GPIO subsystem. Finally, GPIOs are used everywhere. It's a thing that every driver uses, either, not every, but many drivers use either implicitly or explicitly. Implicitly request GPIOs or use resets or use regulators where underneath we're going to use GPIOs. And also many devices next to their primary function, they also register GPIOs with the GPIO lib and export them. So it's no wonder that over the years we have become this. And it's not to say that it's someone's fault in particular. I'm not pointing fingers at anyone, because over so many years, even if you just allowed a very simple workaround here or a trick here, if everyone does it over the years, it simply adds up. GPIO subsystem has had three main, let's say, epochs in its history. So the prehistory is the time where we didn't have anything unified. So every subsystem did something differently. Some symbols would be standardized and used by multiple drivers, but many would add their own extensions or their own symbols. The drivers, because I'm using quotes because this was before the driver model even existed, lived in Arch in every particular platform. Like if you look at the ARM history where we would have Mac this, Mac this, Mac this, many different machines, and all of them would implement something a bit differently. The fallout from it still exists because we still have some of those old platforms implement GPIO drivers in Arch, and just it's basically stitched together with the GPIO subsystem so that it works in a standard way, but it's not. It's far from being correct. Then in 2008, we gained the provider-consumer model. It was based on the half hard-coded, half-dynamic GPIO numbering scheme. This is the one that still exists under the hood in today's GPIO subsystem. This is also the time where the SysFS user space interface has been merged. And the user space interface back then also was based on the same number space. So now we literally cannot get rid of that anymore, or it will take several more years, because user space is used to it, and they will want it to keep on working, including keep the same numbering scheme. So we cannot even change that. And yeah, so this worked like consumers would get numbers, like consumer drivers would get numbers assigned through platform code. They will request the number GPIOs, use them, free them. But the way it was implemented, the fact that we were using numbers means that rogue drivers can simply request some GPIO defined in a header. Like they can say, okay, the GPIO 201 is this, and I want to request it. And nobody would enforce any consumer provider resource assignment because what we're really referring to is numbers. The answer to that is the opaque descriptor-based model, which is the current modern-day standard in the kernel. This means that provider drivers would expose GPIO chips. They would have a certain number of GPIOs, and then through device tree or platform files or ACPI, we would assign GPIOs to consumer drivers or other consumer devices, and they would get opaque handles to structures they can't really access, and using the provided programming interface, they would manipulate them. What's happened, though, is that we have so many users of the old interface that we cannot possibly convert them all at once. So what we do is we support the old interface. The new interface uses the old internals of the new interface uses the old interface internally, or in big part. And what we are doing is we are trying to first convert all the old users to using the new interface. And this has been going on for years. What we have to do is, the new interface is completely different. So you need to convert your board files if they exist, or convert your, add properties to device tree. You need to convert the driver code. Then eventually you switch to the new. You complete your series of switching to the new subsystem, to the new interface. You send those patches. You need to wait for the people who have relevant hardware to test it. Then they will send you feedback and give their tested by tag. And this is where the work is done on that user. But you move to another one, and we cannot remove the old interface until we convert all the users. But even then, once the work in the kernel is done, we're still left with sysfs in the exported user space. We cannot enforce the migration of user space users to the new descriptor-based kernel API if they don't switch. So how do we make it? How do we make everyone switch to the new interface in user space? About that in a minute. So this is the first part of dealing with technical debt in GPIO. We have spent so much effort on converting all the users to the new one, and there's no end in sight because we have so many people, so many drivers still using the old interface that I suppose that the kernel is going to remove support for 32-bit ARM before we actually finish that, and this is going to be how we solve it. So, more technical debt. Initially, you would ask yourself, how difficult can GPIO be? Like, how difficult can toggling pins be? Well, the answer is just as difficult as you want it to be. Initially, when we started, when kernel gained the ability to toggle GPIOs, this was only for GPIOs exposed by SOCs, and they will usually be toggled, in the startup, in the power-up sequence of the board. But eventually, we gained all kinds of use cases, dynamic devices on GPIOs, like GPIO expanders on USBs that you plug in, and then you want to access them from user space. All kinds of situations where you would have expanders, sensors that would, trigger at any point. You need to handle you need to handle interrupts. And this is where, when you have multiple devices and multiple drivers and multiple users, you need to introduce some kind of serialization. some kind of locking. So look at that. What we have here is your typical system as it is today, where you have multiple GPIO drivers. Some of them are MIO drivers. They never sleep. Some of them go over some bus where the transfer enforces sleeping. The users, on the other hand, don't know what kind of GPIOs they're accessing. And the users may want to toggle a GPIO from atomic context, or they may never sleep and toggle it from process context. So this all goes through the same code path through the GPIO lib core. And it turned out that we cannot use spin locks because our drivers may sleep, but we also cannot use mutexes because we may be called from atomic context. This led to all kinds of things, and until recently, you would find stuff like this in GPIO lib, where you would take a spin lock, do something within that lock, then, oh no, I can now call a function that may sleep. So I need to unlock the spin lock. I need to do my sleeping stuff, and I need to reacquire it. So I only released it for a little bit. It can't hurt, right? No state would be re-verified in this case. And if that's not enough, because GPIOs are tightly coupled with pin control, and because GPIO controllers can also be interrupt controllers, we have glue layers to the interrupt subsystem. We have glue layer to pin control. Pin control uses mutexes everywhere because it was not meant to be used from atomic context. On the other hand, the interrupt subsystem will call our GPIO callbacks with a spin lock taken that the spin lock is actually exists in the interrupt subsystem. So this was quite an issue. It's taken me some time to figure it out, and it turns out that a good mechanism for that existed. This was SRCU, which is RCU that allows you to call sleeping functions. Basically, RCU allows you to take read logs from SRCU allows you to take the read. You have to think about it. It's not really a read-write semaphore, but it can be presented in a similar way. So you have read only critical sections, and then you have a mechanism of synchronizing all those read critical sections when you introduce some changes. So the lack of locking in GPIOs started to become a problem. We would have some reports about race conditions, but it was, for the reasons I mentioned, it was very hard to fix. So eventually, and this is the positive point in this presentation, the code has landed for 6.9, where SRCU will be used for enforcing serialization in the GPIO. So this part of technical debt has finally been addressed, and yeah, I'm very happy about it. There is still some issues with the interrupt subsystem where we still have some problems with the GPIO subsystem not being notified about their existing users that had requested interrupts provided by those GPIO chips, but this is something that is left to fix. Anyway, the situation right now is much better than it used to be. Non-exclusive GPIO, so the Krzysztof's favorite. At some point, we had a use case in the regulator subsystem where we needed to provide GPIOs that could be used by multiple users. Because if you don't know, GPIOs can only be requested exclusively. There is no such thing as unlike, for instance, the reset subsystem, a GPIO should only be requested by a single user, either in user space or in the kernel. Not really, because we did introduce a workaround for fixed regulators, and it was supposed to only be used by the regulator subsystem. The non-exclusive GPIOs is, it sounds nice, but it's nothing like what you imagine. What it really is, it simply allows two users to request the same GPIO and then fight over it. No synchronization, no nothing, no reference counting. They basically can say, okay, I'm turning it on. No, I'm turning it off. And it's bad. We didn't catch the fact that other people, even though the comments stated very clearly, this is a workaround for fixed regulators. People started using it, and now you have them all over the kernel, and it's going to be, another couple weeks or months of effort to first find a proper solution, maybe reference counted GPIOs, I don't know yet, find all the users, convert them, and then finally kill this interface. And it's not the only one, because we have other things. Like, for instance, the MMC slot code, handling code, really required a way to toggle the active low setting because of reasons. It was provided for them, marked as, OK, this is a workaround only for the MMC slot code. Bam, and everyone, not everyone, but there are several users now, and we need to get rid of them. There were functions. So initially, we decided that only reading values, setting values, and changing the direction or reading the direction of GPIOs will be allowed to be called from atomic context. Turns out that people started just calling other functions from atomic context. We didn't annotate them with might sleep. Maybe might sleep didn't even exist back then. I'm not sure. We now have functions that are used wrong, even though the documentation states otherwise. And the worst, again, the worst kind of technical debt is when you accrue technical debt in your programming interfaces, but the really worst kind in the kernel is the one that you expose to user space, which one that you cannot just, in the kernel, as long as you have something in the kernel, you can go and fix the instances where it's used and then kill the interface. In user space, it doesn't work like this. This kind of technical debt cannot be improved if paid back, if you will, if the user space doesn't comply. So we have this old sysfs interface for GPIOs. It uses the number space, the old GPIO numbering. We have provided a character device for GPIOs that map the two-level hierarchy that we have, so the chip and the lines underneath. But the users complain about an issue. The issue is that in sysfs, you would have persistence of state. And it's not to say that you don't have that with the character device, because the sysfs is simply a user of GPIOs. It requests GPIOs on behalf of the user space. So you can imagine the sysfs is the program, is the server to which you go and tell, OK, export this one, this GPIO, use it, toggle it, wait for interrupts. But users don't care about the philosophy behind it. They want a persistent state. They want to toggle a GPIO, and they wanted to keep the state. So we need to find a good solution. And the character device has been around for 8 years now, and everyone really complains about the same thing. So I finally decided to manage this technical loan by providing an interface. So I just posted a set of patches that implement a dbus API for GPIO. So you have a daemon that works on behalf of all the users. It provides a well-known protocol and a set of functions. And I should have posted a link here. I think at the time when I was writing it, the patches were not out. But the daemon is now being reviewed. It's still going to take probably some time, at least a couple months. But this is something that I really hope will address the issue and finally will allow people to start switching to the new interface. The Raspberry Pi community actually expressed a rather positive feedback on the dbus API, so hopefully this will allow us to improve the situation on that front. Yeah, so even if we think that from the kernel perspective we have a good solution, our goal is to make the user space happy, because the kernel serves the user space after all. One of the ideas that, this was not mine, this was Linus Valeix who did that, but we had lots of quirks in the GPIO subsystem in different drivers. What Linus did was he went through all of them and basically gathered them in a single file that we have. So, for instance, all the open firmware quirks, various strange ways of handling properties, of handling some weird nodes in device tree, were put into single place. There was actually quite well refactored, and now all the quirks live in a single place. This allows the rest of the code to look much better, and then we have this dark place where you don't venture if you don't have to, where all the weird stuff lives. So, summary. It's impossible to keep technical debt out of a large code base, and let me go back to the question, how difficult can GPIOs be? Well, they can be 10,000 lines of code difficult. This is the level. So toggling pin, and you need 10,000 lines of code to handle that. You will accrue technical debt. And it's hard to catch every user using your interfaces incorrectly. And what you should do is just really filter the code that you're accepting into your subsystem. So it's fine to be grumpy. Don't be bullied into accepting subpar code. I think that the kernel could really use some kind of a good deprecation mechanism for old symbols or symbols that should not be used or symbols that are being used incorrectly. I don't have the answer. If that was my choice, I would probably allow using the GCC's deprecated attribute for functions, but we don't want warnings in our kernel build, and that would result in thousands of warnings. And that's it. So yeah, a few years that I've been doing this, and it's been challenging, but also kind of fun. So you can reach us at linaro.org, or you can write me directly with any questions, send me patches, send me ideas, and time for questions.
So specifically to the SysFS interface, which we all love, of course. I understand we cannot remove it from one day to another for ABI compatibility, but do you think it will be possible that newly added GPIO providers, drivers, do not expose their GPIOs in SysFS? So at some point, users of new devices will be forced to adapt. It doesn't look like a breakage to me, but...
You're not wrong, I guess. Thanks for giving me an idea. I will consider it. I have never thought about it because this is an abstraction level, so I never... I would think that all the citizens of the GPIO driver space should be equal, but who says that, right? Yeah. So yeah, it's a good idea. Yeah, we can definitely consider that.
Well, just the other day, I tried to switch from SysFS to GPIO lib, and I came across exactly this problem that all my user space code needs this persistence. And actually, I needed to stop. It was just not possible because I would have had to rewrite everything or introduce a daemon and, yeah, with dbus, communicate with it. So I really feel that that's a good thing. And I think at that point, when this is there, I could then switch. So I think that's a good way.
So please go to the Linux GPIO mailing list and just test the patches, because that's what I need right now. So the daemon is there. There's a command line client that you can use in your scripts if you're doing scripts, or you can use whatever dbus standardized command line client that you want to use. gdbus is fine. Like this will work because of the standards that that dbus provides. And yeah, if you could test it and send feedback and review, that would be awesome.
Thank you.
Okay. Are there any questions? If not, then going once, going twice. Let's go to the closing game. To jest Bing. Nie, to jest Bing. Wchodzisz na stronę Binga, robisz konto. Tak. Tam możesz generować normalnie. Musisz mieć konto, nie? I masz 15 dziennie obrazków do wygenerowania, bo potem powyżej tego jest płatne. Wpisujesz prompta. Prompt, jaki tam wpisałem, to Nie, włączyłem, mógł ci potem pokazać. Wpisałem po prostu dziwna, steampunkowa maszyna, która wygląda jakby nic do niczego nie pasowało.
It's a mess, but it's